there is a question that has haunted physics for half a century. Not a question about distant galaxies, not a question about the beginning of anything, a question about whether the universe keeps its own records, whether reality, at its most fundamental level, remembers what has happened, whether the past is truly written in indelible ink, or whether it can be erased, completely, permanently, without a trace. The answer should be obvious. Of course the universe remembers. If you burn a piece of paper, the information on that page is not destroyed. It is transformed into ash, into smoke, into infrared radiation spreading outward at the speed of light. The words are gone in any practical sense. You cannot read the page anymore. But in principle, in absolute, unbreakable, mathematically guaranteed principle, every letter could be reconstructed, every curve of every character, every arrangement of every ink molecule. The laws of physics are reversible. Run the equations backward and the paper reassembles. The ink returns. The words reappear, letter by letter, molecule by molecule. This is not a metaphor. It is not a philosophical position. It is a mathematical requirement of quantum mechanics, the most precisely tested theory in the history of science. Information cannot be destroyed. This is the rule. This is the law. And every experiment ever conducted, every single one, across every branch of physics, in every laboratory on Earth, has confirmed it without exception. And then Stephen Hawking showed that black holes destroy it. In 1974, working alone in his office at the University of Cambridge, Hawking published a calculation so elegant and so devastating that it fractured the foundations of theoretical physics. He showed that black holes are not permanent. They radiate. They glow with a faint thermal haze, emitting particles and photons in a slow, relentless stream that never ceases. Over incomprehensible stretches of time, stretches so vast that the current estimated age of the universe is an eye blink by comparison. This radiation drains the black hole of its mass. The black hole shrinks. It gets hotter as it shrinks. It radiates faster as it gets hotter. And eventually, after an interval of time so long that no human number system was designed to express it, it vanishes entirely, gone. And with it, according to Hawking's mathematics, checked and rechecked by every major theoretical physicist on Earth for decades, every scrap of information it ever consumed, every star it swallowed, every planet it devoured, every atom, every photon, every quantum state that ever crossed its event horizon, all of it permanently erased, as if it never existed, as if the universe itself had forgotten. One law says information cannot be destroyed. Another law says black holes destroy it. Both laws have been tested with extraordinary precision. Both laws have never been contradicted by a single experiment, and both laws cannot simultaneously be true. This is the black hole information paradox. It is not a minor puzzle. It is not a technicality hiding in the margins of a textbook that only specialists care about. It is a direct, violent contradiction between the two pillars upon which all modern physics is built, quantum mechanics and general relativity. One of them is wrong, or both of them are incomplete, or something deeper and stranger is happening that neither theory on its own can describe. And for 50 years, no one has been able to determine which. This paradox has consumed some of the most brilliant minds on Earth. It sparked a legendary bet between Hawking and the Caltech physicist John Preskill, a bet whose stakes were an encyclopedia, deliberately chosen as a symbol for the vast store of information at risk. It led to the proposal that the inside of a black hole might be a wall of fire, hot enough to vaporize anything that crosses the event horizon. It generated the extraordinary idea that entangled quantum particles might be connected by tiny, non-traversable wormholes threading through the fabric of space-time. It suggested that the three-dimensional universe we inhabit might be a holographic projection from a distant two-dimensional surface we can never see or touch. And it forced physicists to confront a possibility so radical that many still resist it, that space and time themselves are not fundamental features of reality, but emergent illusions arising from something deeper, something that has no shape, no extension, no duration, something made of pure quantum information. The stakes could not be higher. If Hawking was right, and information truly can be destroyed, then the fundamental equations of quantum mechanics are wrong. Not approximately wrong. Not wrong in some obscure corner case that never matters in practice. Wrong in principle. And if those equations are wrong, then every prediction they have ever made, every atom they have described, every chemical bond they have explained, every transistor in every computer on Earth rests on a foundation that contains a fatal crack. By the end of tonight, you're going to understand exactly why this paradox is so devastating. You are going to follow the chain of logic that connects a quiet calculations about radiation from a dying black hole to the unraveling of space-time itself. You will see each attempted solution: complementarity, holography, firewalls, ER equals EPR, the island formula, and you will understand why none of them has fully succeeded. And when we reach the end, you may find that the information paradox is not just about black holes. It is about you, about whether the atoms in your body carry an indelible record of their history, about whether the universe, at its most fundamental level, is a system with perfect memory, about whether anything at all, can truly be forgotten. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand why the information paradox cuts so deep, you first need to understand the object at its center. Not the popular image, not the swirling disk of light from a science fiction film, not the artist's rendering with neatly labeled arrows showing matter spiraling inward. The real thing. What a black hole actually is, according to the equations that describe it, and what it does to the space and time around it. A black hole is a region of spacetime where matter has been compressed so completely that the gravitational pull it generates prevents anything from escaping. Not just matter, not just gas and dust and rock. Light, the fastest entity in the known universe. The cosmic speed limit that nothing with mass can ever reach, and that even massless particles travel at, but never exceed. Even light, traveling at roughly 300,000 kilometers per second, cannot climb out of a black hole. And the reason is not some exotic force pulling it back. The reason is far stranger, far more disturbing. The black hole has warped the very geometry of space and time so severely that every possible path, every direction, every trajectory, every conceivable route an object or a photon could take, curves back inward. There is no outward direction anymore. The concept of away from the black hole ceases to have meaning inside the event horizon. The exit has been removed from the architecture of space itself. Not blocked, removed. It does not exist. Think about what that implies. Stand on the surface of the Earth and throw a ball straight up. If you throw it fast enough, about 11.2 kilometers per second, which is roughly 40,000 kilometers per hour, it will escape Earth's gravity entirely and fly off into space. This speed is called the escape velocity. Every massive object has one. For the Moon, it is lower, roughly 2.4 kilometers per second. For Jupiter, it is about 59.5 kilometers per second. For the Sun, it is much higher, approximately 618 kilometers per second. The more massive and compact the object, the higher the escape velocity at its surface. Now imagine compressing the Earth, taking all 5.97 times 10 to the 24th kilograms of it, every mountain, every ocean, every grain of sand, and squeezing it down, smaller and smaller, past the size of a basketball, past the size of a golf ball, past the size of a pea, down to a sphere roughly 1.7 centimeters across, smaller than a marble. The mass would be identical, but the escape velocity at the surface of this compressed Earth would reach 300,000 kilometers per second, the speed of light. And since nothing in the universe can travel at or beyond the speed of light, nothing would escape. The compressed Earth would have become a black hole. Its event horizon, the boundary beyond which escape is impossible, would be that marble-sized sphere 1.7 centimeters in diameter. That compression is violent beyond comprehension. The density at the event horizon would be approximately 5.5 times 10 to the 27th kilograms per cubic meter. To put that in perspective, the density of lead is about 11,000 kilograms per cubic meter. The density of a neutron star, the densest stable object in the known universe, is about 10 to the 17th kilograms per cubic meter. The density needed to compress Earth into a black hole exceeds even neutron star density by 10 billion times. But here is the part that violates your intuitions about density. For larger black holes, the average density at the event horizon is actually lower, much lower, dramatically lower. A supermassive black hole with a mass of 4 billion suns has an average density at the event horizon comparable to that of water. A black hole with 10 billion solar masses has an average density at the event horizon less than that of air. You could cross the event horizon of such a black hole and feel nothing. No crushing pressure, no tidal forces tearing you apart. The space around you would seem perfectly ordinary. The stars above you might still be visible. Your instruments might register nothing unusual at all. And yet, you would never return. You would have crossed a boundary that cannot be uncrossed, a threshold that exists not as a wall or a barrier, but as a property of the geometry of spacetime itself. The event horizon is not a surface. It is not a membrane. It is not anything you can touch or see or feel. It is a mathematical boundary, a sphere in spacetime beyond which all world lines, all possible trajectories, all conceivable paths through space and time lead inward. Cross it, and the radial coordinate, the direction that used to point outward, away from the center, becomes timelike. Moving away from the center becomes as impossible as moving backward in time. You cannot choose not to fall inward any more than you can choose not to move forward in time. The future, for anything inside the event horizon, points in one direction only: inward, toward the center, toward the singularity. There is no way out. Now scale upward. The Sun contains approximately 333,000 times the mass of Earth. If the Sun were compressed into a black hole, its event horizon would be roughly 6 kilometers across. A sphere 6 kilometers in diameter. You could walk across it in an hour. It would contain the entire mass of the star that lights our solar system. And nothing inside that 6-kilometer sphere would ever be seen or heard or detected again. The black hole at the center of our own galaxy is called Sagittarius A star. It contains roughly 4 million times the mass of the Sun. Its event horizon stretches approximately 24 million kilometers across. That is about 17 times the diameter of the Sun. Imagine 17 suns lined up side by side. That is the width of this single object's point of no return. And yet Sagittarius A star is modest by supermassive black hole standards. It is, comparatively, a small one. The black hole at the center of the galaxy Messier 87, the one famously imaged by the Event Horizon Telescope collaboration in 2019, producing the first direct visual evidence of a black hole's shadow, contains approximately 6.5 billion solar masses. Its event horizon is larger than our entire solar system. The orbit of Pluto, the outermost traditionally recognized planet, fits comfortably inside. Every planet, every asteroid, every comet in the Oort cloud, every grain of interplanetary dust, all of it could be swallowed without the event horizon noticing. And then there is the black hole in the galaxy NGC 4889, estimated at roughly 21 billion solar masses. Its event horizon spans a region so vast that light would take days to cross it. 21 billion times the mass of the Sun, packed behind a boundary from which nothing returns. The numbers are striking, but numbers alone do not capture what makes a black hole fundamentally different from every other object in the cosmos. A neutron star is dense. A white dwarf is compact, but they are still objects. They have surfaces. They have edges you could, in principle, stand on. They emit light. They interact with the universe around them in ways that can be observed and measured. A black hole has no surface. It has an event horizon, which is not a physical thing. It is a geometric property of space-time, and beyond the event horizon, at the very center, lies something that breaks physics entirely: the singularity. According to general relativity, Albert Einstein's theory of gravity, published in 1915 and confirmed by every gravitational experiment conducted in the centuries since, at the center of every black hole lies a point of infinite density, infinite curvature. The equations that describe the smooth fabric of space-time produce outputs of infinity, and in physics, infinity is not a result, it is a distress signal. It means the theory has exceeded its domain of validity. It means something is happening that the mathematics cannot capture. The singularity is not a prediction of what exists. It is a confession that we do not know what exists. The history of how humanity came to understand these objects is a story of ideas too radical to accept, dismissed by the greatest minds of their era, and ultimately confirmed by the universe itself. The first glimmer of the idea appeared in 1783. John Michell, an English clergyman and natural philosopher, a man who also invented the torsion balance and made foundational contributions to the study of earthquakes, used Newton's laws of gravity to calculate that a star of sufficient mass and sufficient compactness would have an escape velocity exceeding the speed of light. He called it a dark star. Such an object would emit no light. It would be invisible. The idea was published in the Philosophical Transactions of the Royal Society, and then, for more than a century, essentially vanished from scientific discourse. Pierre-Simon Laplace independently proposed a similar concept in 1796, then quietly removed it from later editions of his work, apparently uncomfortable with its implications. The modern theory begins with Karl Schwarzschild. In January of 1916, barely 2 months after Einstein published the final form of his field equations of general relativity, Schwarzschild, a German physicist serving on the Eastern Front during the First World War, found the first exact analytical solution. Working in the trenches, ill with a disease that would kill him within months, he derived the geometry of spacetime around a perfectly spherical, non-rotating mass. His solution was beautiful and exact, and embedded within it was a disturbing feature. At a certain radius, now called the Schwarzschild radius, a component of the metric tensor diverged. The mathematics behaved strangely. Time, as measured by a distant observer, appeared to freeze for an object approaching that radius. Light from the infalling object would stretch to infinite wavelength, redshifting until it faded below detectability. Schwarzschild had discovered the event horizon. He died in May of 1916, never knowing what his solution truly implied. Einstein was troubled. He did not believe nature would permit such an object. In 1939, he published a paper explicitly arguing that matter could not be compressed to the point where a Schwarzschild singularity would form. Arthur Eddington, the astronomer who had confirmed Einstein's prediction of light bending around the sun during the solar eclipse of 1919, called the idea of complete gravitational collapse absurd. He declared that there should be a law of nature preventing a star from behaving in so unreasonable a fashion. The physics establishment was united. Black holes were mathematical curiosities, not physical realities, and no one saw it coming. The universe did not consult the establishment. In 1930, a 20-year-old Indian physicist named Subramanian Chandrasekhar boarded a ship from Bombay to Cambridge. During the 18-day sea voyage, he performed a calculation that would change the course of astrophysics. Combining the new quantum mechanics with special relativity, he showed that a white dwarf star, the dense remnant left when a star like our Sun exhausts its nuclear fuel, could only resist gravitational collapse if its mass remained below a critical threshold. That threshold, now called the Chandrasekhar limit, is approximately 1.4 solar masses. Above that limit, the quantum degeneracy pressure of electrons, the force that holds a white dwarf up against gravity, is insufficient. Gravity wins. The star must collapse further. To what? Chandrasekhar did not specify, but the implication was clear. For stars above the limit, no known force could prevent continued collapse. Chandrasekhar presented his result to the Royal Astronomical Society in January of 1935. Eddington stood up immediately afterward and ridiculed the finding. The humiliation was public and devastating. Chandrasekhar later described it as the most painful experience of his scientific career. He eventually left England for the University of Chicago, but the mathematics was correct. The Chandrasekhar limit stands unmodified to this day. Chandrasekhar received the Nobel Prize in Physics in 1983, nearly 50 years after the discovery. Eddington received no Nobel Prize. In 1939, the same year Einstein published his skeptical paper, J. Robert Oppenheimer and his student Hartland Snyder published a paper titled On Continued Gravitational Contraction. They showed, using Einstein's own field equations, that a sufficiently massive star, having burned through its nuclear fuel, would collapse past the Schwarzschild radius. Nothing in known physics could stop it. No force, no pressure, no quantum effect could resist the inward pull of gravity beyond a certain point. The star would shrink below its event horizon and continue collapsing indefinitely to a point, a singularity, surrounded by a region of space-time from which nothing, not light, not matter, not information, could ever escape. The term black hole did not yet exist. That phrase was popularized in 1967 by the American physicist John Archibald Wheeler. Wheeler had initially been skeptical of total gravitational collapse, but he came to understand that the event horizon was not a pathology of the mathematics. It was a feature of reality, and the name he gave it, black hole, captured something essential about its nature, a region of absolute darkness, of absolute finality. The theoretical breakthrough came in 1965. Roger Penrose, a British mathematician working at Birkbeck College in London, and published a singularity theorem that transformed the field. Using techniques from differential geometry and topology, Penrose proved that once a trapped surface forms, a closed surface from which all outward-directed light rays converge inward rather than diverge outward, the formation of a singularity is inevitable, not under special circumstances, not in artificially simplified scenarios. Under very general physical conditions, with minimal assumptions about symmetry, gravitational collapse, once it passes the point of no return, leads unavoidably to a singularity. The theorem was powerful because it was nearly assumption-free. Penrose received a share of the Nobel Prize in Physics in 2020 for this work, more than 55 years after publication. Stephen Hawking, a young physicist at Cambridge, collaborated with Penrose throughout the late 1960s. Together they extended the singularity theorems to show that singularities are generic features of general relativity, not anomalies, not edge cases, fundamental consequences of the theory. Their joint work established the mathematical bedrock upon which all subsequent black hole physics would rest. The universe contains several types of black holes, each born from different cosmic violence. Stellar mass black holes form when massive stars die. A star exceeding roughly 20 to 25 solar masses, having exhausted its nuclear fuel, can no longer support itself against gravity. The core collapses. The outer layers are ejected in a supernova explosion, one of the most energetic events in nature, briefly outshining an entire galaxy of hundreds of billions of stars. If the remaining core exceeds roughly 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, above which neutron degeneracy pressure also fails, it collapses to form a black hole. These stellar mass black holes typically contain between about 5 and several tens of solar masses. According to scientific estimates, our galaxy alone may harbor on the order of 100 million of them. Most are invisible, drifting silently through the galactic disk, detectable only when they gravitationally interact with a companion star or merge with another compact object. Those mergers have now been directly detected. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from 2 stellar mass black holes spiraling together and merging. The black holes had masses of roughly 36 and 29 solar masses. They combined to form a single black hole of approximately 62 solar masses. The missing 3 solar masses were converted entirely into gravitational wave energy, ripples in the fabric of spacetime itself. In a fraction of a second, that merger released more energy than all the stars in the observable universe were emitting at that moment. Combined, the signal that LIGO detected was a tiny stretching and squeezing of space, a change in the length of its 4-kilometer detector arms by less than 1,000th the width of a proton. The detection confirmed general relativity's prediction of gravitational waves made a century earlier and opened an entirely new observational window on the cosmos. Supermassive black holes are the titans. They reside at the centers of most, and perhaps all, large galaxies. They contain millions to billions of solar masses. How they form is debated. Some models suggest they grew from stellar mass seeds that merged and accreted matter over immense timescales. Others propose they formed from the direct gravitational collapse of massive primordial gas clouds in the early universe, bypassing the stellar stage entirely. Observations of quasars, galaxies with extremely luminous, actively feeding supermassive black holes at their centers, at very high redshifts suggest that some supermassive black holes grew to billions of solar masses remarkably quickly, challenging many formation models. There is also a speculative third category, primordial black holes. These hypothetical objects could have formed from extreme density fluctuations in the very early universe. Unlike stellar or supermassive black holes, they would not require the collapse of a star. They could span a vast range of masses, from far below a solar mass to thousands of solar masses. None have been definitively detected, but their possible existence is profoundly relevant to our story, because the smallest primordial black holes, if they exist, could already be evaporating through Hawking radiation. Right now, somewhere in the cosmos, a primordial black hole the mass of a small asteroid might be in the final stages of its life, growing hotter and hotter, radiating faster and faster, approaching its last explosive moment. Before we confront the paradox, one more concept demands careful explanation: the concept of information in physics. This is not information in the everyday sense, not data on a hard drive, not words on a page, not anything you would recognize as information in ordinary life. In physics, information is the complete quantum mechanical description of a system. Every particle has a quantum state, a set of properties including its position, momentum, spin, charge, and polarization. The quantum state of a system is the totality of these properties for every particle the system contains. And the fundamental law of quantum mechanics, expressed mathematically through a property called unitarity, demands that this quantum information is conserved, always, under every circumstance, without exception. Unitarity means that the equations of quantum mechanics are reversible. The evolution of a quantum system from one state to another is described by a unitary operator. A unitary operator is, by definition, invertible. Run it forward, and you get the future state. Run it backward, and you recover the past state perfectly. No information is lost in either direction. The future contains everything the past contained. The past can be reconstructed from the future with perfect fidelity. If you burn a book, the information in that book is not destroyed. It is scattered, redistributed among the ash particles, the smoke molecules, the photons of infrared light, the convection currents in the air. The redistribution is so thorough that no practical measurement could ever reassemble the book. But in principle, with godlike knowledge of every outgoing particle, you could reverse the process, page by page, letter by letter, ink molecule by ink molecule. The information was never destroyed, it was transformed. This is not a philosophical preference. Violate unitarity, and the probabilities predicted by quantum mechanics no longer sum to 1. A probability that does not sum to 1 is not a probability at all. The theory becomes inconsistent. Prediction becomes impossible. The entire framework, the framework that describes every atom, every chemical reaction, every transistor, every laser, every MRI machine, every nuclear reactor on Earth, that framework collapses. Unitarity is not a feature of quantum mechanics. It is the spine. To make the strangeness of black holes visceral, consider what would happen to a human body falling into one. For a stellar mass black hole, say 10 solar masses, the tidal forces near the event horizon are extreme. Gravity pulls harder on the parts of your body closer to the center than on the parts farther away. The difference in gravitational acceleration across a 2-meter-tall human body near a 10 solar mass black hole would be lethal well before the event horizon is reached. Your body would be stretched lengthwise and compressed widthwise. Physicists have a name for this process: spaghettification. It is not a euphemism. The body would be drawn into a long, thin strand of matter, like spaghetti, before being ripped apart at the atomic level. The tidal forces would separate molecules, then atoms, then the nuclei of atoms themselves. By the time the remnants crossed the event horizon, what was once a human being would be an elongated stream of subatomic particles falling inexorably inward. For a supermassive black hole, the situation is different. The tidal forces at the event horizon of a billion solar mass black hole are gentle. A human could cross the event horizon without feeling any discomfort at all. No stretching, no compression, no indication whatsoever that the most consequential boundary in the universe had just been crossed. The destruction would come later, deeper inside, as the tidal forces increase without bound on the approach to the singularity. Now consider time dilation. General relativity predicts that time flows more slowly in stronger gravitational fields. Near a black hole, this effect is extreme. Imagine hovering just outside the event horizon of Sagittarius A star, say, at a distance of 1 Schwarzschild radius above the horizon. Time for you would pass at a crawl relative to a distant observer. 1 hour of your time might correspond to years, centuries, or millennia of time passing for someone watching from far away. The closer you hover to the horizon, the more extreme the dilation becomes. At the horizon itself, in the mathematical limit, time stops entirely from the perspective of the distant observer. An object falling toward the horizon appears to slow down, redshift, and fade, never quite reaching the boundary, hovering there for eternity in an ever dimmer, ever redder ghost image. But from the perspective of the falling object itself, the crossing happens in finite time. There is no pause, no hovering. You fall through at speed, and the universe above you appears to accelerate. Stars brighten, age, and die in what feels like moments. The two perspectives, the distant and the local, are both correct. They are both valid descriptions of the same physical reality, and they are fundamentally incompatible. This incompatibility, as we will see, lies at the very heart of the information paradox. There is another observational milestone that must be mentioned. In April of 2019, the Event Horizon Telescope Collaboration, a planet-spanning network of radio telescopes linked together to form an Earth-sized virtual telescope, released the first image of a black hole shadow. The target was Messier 87's supermassive black hole, 6.5 billion solar masses, 55 million light-years away. The image showed a bright ring of superheated gas surrounding a dark central region, the shadow of the event horizon. It was not a photograph in the conventional sense. It was a reconstruction from radio frequency data collected by 8 telescopes across 4 continents. But it was real. The shadow was real. The ring was real. The black hole, predicted by mathematics over a century earlier and dismissed as impossible by Einstein himself, was staring back at us from the center of a distant galaxy. In 2022, the collaboration released a second image, this time of Sagittarius A star, the black hole at the center of our own Milky Way, 4 million solar masses, 26,000 light-years away, our own galactic heart, beating in darkness. And there is one more detection that must be understood in its full weight. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the gravitational waves produced by 2 stellar mass black holes spiraling into each other and merging. The black holes had masses of roughly 36 and 29 solar masses. They spiraled inward, orbiting each other hundreds of times per second in the final moments, and merged to form a single black hole of approximately 62 solar masses. The missing 3 solar masses, an amount of matter equivalent to 3 entire suns, were not absorbed. They were radiated away, converted entirely into gravitational waves, pure ripples in the fabric of space-time, propagating outward at the speed of light. In a fraction of a second, that merger released more energy than all the stars in the observable universe were emitting at that moment combined. The signal traveled 1.3 billion light-years across the cosmos and arrived at Earth as a subtle stretching and squeezing of space itself, a displacement smaller than 1,000th the diameter of a proton, and LIGO measured it. 2 4-kilometer-long laser interferometers, one in Livingston, Louisiana, and one in Hanford, Washington, simultaneously detected the signal. It matched the predictions of general relativity with extraordinary precision. The waveform, the shape of the signal as a function of time, was exactly what Einstein's equations predicted for 2 black holes spiraling into each other. A century-old prediction, confirmed. An entirely new window on the cosmos opened. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, along with the mergers of neutron stars and mixed systems. Each detection provides another test of general relativity in the strong field regime, the regime where gravity is most extreme, most nonlinear, and most relevant to the information paradox. There is also a speculative but important third category of black holes, primordial black holes. Unlike stellar mass and supermassive black holes, which form from the collapse of matter in the present-day universe, Primordial black holes could have formed in the extreme conditions of the very early universe, in the first fractions of a second after the initial expansion began. Density fluctuations in the hot dense plasma of the early cosmos could, if sufficiently large, have collapsed directly into black holes without needing a star to die first. These primordial black holes could span a vast range of masses, from far below a solar mass, perhaps as small as a mountain or even lighter, to thousands of solar masses. None have been definitively detected. Their existence remains hypothetical, but they matter enormously for our story, because the smallest primordial black holes, if they exist, could already be evaporating through Hawking radiation. A primordial black hole with an initial mass of roughly 5 times 10 to the 11th kilograms, comparable to the mass of a small asteroid, would have a Hawking temperature high enough that it would be reaching the final stages of evaporation right now in the present epoch. Its final moments would produce a burst of high-energy gamma rays. Searches for these bursts have been conducted. None have been found. But the absence of detection does not mean primordial black holes do not exist. It means either they are rare, or they formed with masses large enough that they have not yet evaporated. The question remains open. And if even one primordial black hole is evaporating somewhere in the cosmos right now, the information paradox is not merely a thought experiment about the far future. It is a process unfolding in real time, and Hawking showed that these objects, these monuments of gravitational finality, snap the spine of quantum mechanics. They erase information permanently, irrecoverably, without leaving any trace in the radiation they emit as they slowly die. The stage was set for the most profound crisis in modern theoretical physics, a clash not between theories and experiments, but between two theories, both confirmed by experiment to extraordinary precision, that contradict each other at the most fundamental level. Something had to give, something fundamental, something sacred. But what scientists discovered next was worse than anyone expected. The year was 1973. Stephen Hawking traveled to Moscow to meet two Soviet physicists, Yakov Zeldovich and Alexei Starobinsky. They had been studying the quantum properties of rotating black holes, and they had arrived at a surprising conclusion. A rotating black hole, they claimed, should spontaneously emit particles. Not from its interior, nothing escapes from there, but from the violently twisted space-time just outside the event horizon. The process was analogous to the way a spinning conductor emits electromagnetic radiation. Hawking found the claim intriguing but suspected an error in the details. He returned to Cambridge and set about proving them wrong. He proved something far more alarming. Using the mathematical framework of quantum field theory applied to curved spacetime, a framework he had helped develop, Hawking demonstrated that the emission was not limited to rotating black holes. All black holes radiate, every single one. A perfectly spherical, non-rotating, electrically neutral black hole sitting alone in otherwise empty space will emit a steady, faint stream of particles. The emission has a thermal spectrum. It looks exactly like the radiation from a hot object. The black hole has a temperature. It glows, faintly, constantly, relentlessly. The paper was published in 1974 in the journal Nature under the title Black Hole Explosions. The question mark in the title belied the certainty of the result. The calculation was elegant, rigorous, and devastating. It did not merely predict a new phenomenon. It exposed a contradiction at the heart of physics that remains unresolved to this day, and it did so with a mathematical clarity that left virtually no room for escape. Here is how Hawking radiation works at its most fundamental level. Quantum mechanics tells us that empty space is never truly empty. Even in a perfect vacuum, a region containing no particles, no matter, no radiation whatsoever, quantum fields fluctuate. These fluctuations manifest as pairs of virtual particles, a particle and its antiparticle that briefly pop into existence and then annihilate each other almost instantly. They borrow energy from the vacuum, exist for an interval dictated by the Heisenberg uncertainty principle, then return that energy by mutually destroying each other. This process is continuous. It happens everywhere. It is happening in the space around you right now, between you and the walls, between your fingers, in the empty spaces between the atoms in your bones. Virtual particles are not exotic. They are as fundamental as the vacuum itself. Now place this process near the event horizon of a black hole. A virtual particle pair appears just outside the horizon. Under normal circumstances, the pair would annihilate. But the gravitational tidal forces near the event horizon are extreme. The curvature of space-time is so severe that occasionally, rarely, but with the probability that is precisely calculable, the pair is torn apart before annihilation can occur. One particle falls inward, crossing the event horizon. The other escapes outward, flying away from the black hole with real positive energy. It is important to be precise here. The virtual particle picture, while vivid and useful, is a simplified description. The rigorous derivation of Hawking radiation uses the formalism of quantum field theory in curved space-time and does not depend on the virtual particle interpretation. Hawking computed the Bogolyubov coefficients relating the vacuum state as defined by an observer in the distant past to the vacuum state as defined by an observer in the distant future. He showed that what the past observer calls a vacuum, empty space, the future observer sees as a thermal bath of particles. The radiation is not emitted from any particular location. It emerges from the quantum mechanical structure of the vacuum in the curved spacetime geometry near the event horizon. The particles are real, the radiation is real, but the mechanism is inherently quantum mechanical, a consequence of the incompatibility between the notion of particle in different reference frames in curved space-time. Energy must be conserved. The escaping particle carries positive energy into the universe. That energy must come from somewhere. It comes from the black hole itself. The infalling partner effectively carries negative energy into the black hole, reducing its total mass. The black hole has lost a tiny amount of mass, a single particle's worth. But multiply this by the relentless, ceaseless passage of time, years, millennia, eons, epochs stretching beyond the capacity of language to describe, and the effect accumulates. The black hole is evaporating. It is worth pausing to appreciate the timescales involved, because they are among the most extreme numbers encountered anywhere in physics. A black hole with the mass of our Sun has a Hawking temperature of approximately 60 billionths of a Kelvin, 60 nanokelvin. For context, the coldest temperature ever achieved in a laboratory on Earth is roughly 100 trillionths of a Kelvin, about 100 picokelvin, achieved in ultra-cold atomic experiments using laser, cooling, and evaporative techniques. The Hawking temperature of a solar mass black hole is several hundred times warmer than that, but still almost immeasurably cold by any everyday standard. It is vastly colder than the cosmic microwave background radiation, which currently sits at approximately 2.7 Kelvin. The afterglow of the earliest epoch of the universe, cooled by 13.8 billion years of cosmic expansion. This means that a solar mass black hole, right now, is absorbing far more energy from the cosmic microwave background than it emits through Hawking radiation. It is gaining mass, not losing it. It is growing, not shrinking, for now. But the cosmic microwave background cools as the universe expands. It has been cooling since the universe began and will continue to cool, asymptotically approaching absolute zero over immense timescales. Eventually, in the extraordinarily distant future, the background temperature will drop below the Hawking temperature of stellar mass black holes, and then, particle by particle, photon by photon, those black holes will begin their long, slow evaporation. How long? For a solar mass black hole, the evaporation time is approximately 10 to the power of 67 years. That number is so large that it resists meaningful comparison. The current estimated age of the universe is roughly 13.8 billion years. Call it 10 to the power of 10 years, in round numbers. The evaporation time for a solar mass black hole is not merely millions or billions of times longer. It is 10 to the power of 57 times longer than the current age of the universe. If you wrote out the number of years as a 1 followed by zeros, the string of zeros alone would stretch 67 digits. No human number system was designed for such a quantity. No analogy carries its weight. For supermassive black holes, the timescale grows even more staggering. A black hole with 1 billion solar masses, comparable to the black hole at the center of Messier 87, would take approximately 10 to the power of 100 years to evaporate. That is a Google years, a 1 followed by 100 zeros, a duration so vast that the entire thermal history of the universe, from the first fraction of a second through the formation of atoms, the birth and death of every star that will ever shine, and the final cooling of the last white dwarfs into black dwarfs, occupies an imperceptibly small fraction of it. But, and this is the point Hawking grasped immediately, the evaporation time is finite, not infinite. Finite. Every black hole, given sufficient time, will evaporate completely. It will shrink and shrink, its temperature rising as its mass decreases. Because smaller black holes are hotter, an inverse relationship that accelerates the evaporation as the black hole gets smaller. In the final moments, as the black hole approaches the Planck mass, approximately 22 micrograms, the evaporation becomes explosive. The temperature skyrockets, the radiation output surges, the last remnants of mass are radiated away in a burst of high-energy particles, a tiny but genuine detonation, and then it is gone, completely. Nothing remains where the black hole once was. And when it is gone, what has it left behind? Hawking radiation, a diffuse cloud of thermal particles dispersing into the vacuum. And this is where the paradox strikes with its full, devastating force. Thermal radiation is featureless. It is the most random, most structureless form of energy in all of physics. A thermal spectrum is characterized by a single number, its temperature. Nothing else. It does not matter what fell into the black hole. It does not matter whether the black hole consumed a star made of hydrogen, or a planet made of iron, or a spacecraft carrying the complete works of every author who ever lived. The Hawking radiation that emerges is identical, a perfect black spectrum at the Hawking temperature, the same regardless of what went in. The radiation carries no imprint, no fingerprint, no record whatsoever of the matter that formed the black hole or the matter that fell into it afterward. This means the information is gone, not merely hidden, not merely scrambled beyond practical recovery, gone. The quantum states of everything the black hole consumed, the exact positions, momenta, spins, charges, and polarizations of every single particle have been permanently erased from the universe. The cosmic ledger has been wiped. If you burned a book, you could, in principle, reconstruct it from the ash and the smoke and the light. But if you threw a book into a black hole and waited for the black hole to evaporate, there would be nothing left. Nothing in the radiation, nothing in the vacuum, nothing anywhere from which the book could be reconstructed, not even in principle. The information does not exist anymore, anywhere, and it gets worse. Because the destruction of information is not merely a violation of a useful rule, it is a violation of the foundational structural principle of quantum mechanics, unitarity. The mathematical property that ensures the equations of quantum mechanics are reversible, that probabilities sum to 1, that the future is determined by the past, and the past can be recovered from the future. If unitarity is violated, quantum mechanics collapses. Not approximately, not in an edge case. Fundamentally, the probabilities predicted by the theory would no longer be guaranteed to sum to unity. Prediction, the core activity of all science, would become impossible. The framework that describes every atom, every chemical reaction, every semiconductor, every laser, every nuclear reactor, every biological process on Earth, that framework would fail. Here is the paradox stated as cleanly as possible. 3 principles of physics, each individually confirmed by overwhelming experimental evidence, cannot all be simultaneously true in the presence of a black hole that forms and then evaporates. The first principle is the equivalence principle, the foundation of general relativity. It states that a freely falling observer experiences no local effects of gravity. If you fall toward a black hole and cross the event horizon, you notice nothing special at the moment of crossing. No wall, no barrier, no alarm, no flash of light. The event horizon is not a physical surface. It is a global feature of space-time geometry, detectable only by a distant observer. Physics at the horizon, for someone falling through, looks perfectly ordinary. The equivalence principle is not a minor feature of general relativity. It is the principle upon which the entire theory is built. Every prediction of general relativity, the bending of starlight, the precession of Mercury's orbit, the the dilation of time in gravitational fields, the existence of gravitational waves, rests on this principle. Abandon it, and general relativity crumbles. The second principle is unitarity. Quantum mechanics demands that the evolution of any quantum system is described by a unitary operator, an operator that is, by mathematical definition, reversible. The output state contains all the information of the input state. No information is created, no information is destroyed. If unitarity is violated, quantum mechanics fails as a consistent theory, not just for black holes, for everything. The third principle is that the physics outside the black hole, in the region accessible to a distant observer, is well described by effective quantum field theory. This is the framework that undergirds the standard model of particle physics. Applied to the region outside the event horizon, it predicts that the Hawking radiation is thermal, structureless, devoid of information about the black hole's interior or history. This framework has been tested in particle accelerator experiments with extraordinary precision. In some cases, predictions have been confirmed to better than 1 part in 10 billion. Now here is the trap that makes the paradox inescapable. If the equivalence principle holds, nothing special happens at the event horizon. An infalling observer passes through smoothly. If unitarity holds, the information about everything that fell in must somehow get out, encoded in the Hawking radiation. If effective field theory holds outside the horizon, the Hawking radiation is thermal and carries no information. You can have any two, you cannot have all three. Something must break. And every proposed resolution to the information paradox amounts to choosing which principle to sacrifice, which pillar of modern physics to tear down. And whatever you tear down must be replaced with something at least as powerful, at least as well tested, and at least as mathematically consistent as what you destroyed. This is the part that keeps physicists awake, because each of these three principles has been confirmed by experiment to an extraordinary degree. General relativity has been verified by every gravitational observation ever made. From the perihelion precession of Mercury, measured to match Einstein's prediction within experimental error, to the detection of gravitational waves by LIGO in 2015, matching the predicted waveform of merging black holes with exquisite precision. Quantum mechanics has been confirmed by every atomic and subatomic experiment ever conducted. It is the most precisely tested theory in the history of science. Effective field theory is the foundation of the Standard Model, which predicted the existence of the Higgs boson decades before its discovery at the Large Hadron Collider in 2012. And yet, in the vicinity of a black hole, they cannot all be correct. The universe, in this one extraordinary context, forces a choice, and the correct choice remains unknown. The paradox deepens further when you consider the thermodynamic nature of black holes, a connection that adds a second layer of crisis to the first. In 1972, a year before Hawking travelled to Moscow, the Israeli-American physicist Jacob Bekenstein proposed something audacious. He suggested that black holes have entropy. In thermodynamics, entropy is a measure of microscopic disorder. More precisely, it quantifies the number of distinct microscopic configurations, or microstates, that are consistent with a system's macroscopic appearance. A cup of hot water has high entropy because the water molecules can be rearranged in a vast number of ways without changing the cup's temperature, pressure, or volume. Bekenstein argued that a black hole too has entropy, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This was deeply strange. In every other known physical system, entropy scales with volume. Double the size of a box, and you double the number of possible microstates. But for a black hole, the entropy, the information content, the count of microstates, scales with the surface area. Bekenstein proposed this scaling tentatively. Hawking, initially skeptical of Bekenstein's proposal, inadvertently confirmed it through his radiation calculation. The result, now known as the Bekenstein-Hawking entropy formula, states that the entropy of a black hole equals the area of its event horizon divided by 4 times the Planck area. The Planck area is the square of the Planck length, approximately 2.6 times 10 to the negative 66 square centimeters. An area so microscopically tiny that it bears the same ratio to a single atom as a single atom bears to the entire observable universe. The entropy implied by this formula is staggering. A solar mass black hole has a Bekenstein-Hawking entropy of approximately 10 to the power of 77 in Planck units. For perspective, the total entropy of all ordinary matter in the observable universe, every star, every planet, every nebula, every gas cloud, is estimated at roughly 10 to the power of 88. A single supermassive black hole can rival or exceed the entropy of every visible object in the cosmos. Black holes are, in a precise and quantifiable thermodynamic sense, the most disordered objects in the universe. They contain more microscopic information, more possible internal arrangements, than anything else of comparable size. But here is the devastating question that Bekenstein's result raises. If a black hole has an entropy of 10 to the 77th, then according to the principles of statistical mechanics, that entropy must correspond to actual microstates, actual microscopic degrees of freedom, actual physical configurations, actual information. Where is all of that information stored? It cannot be at the singularity. The singularity is a point where our theories break down, not a location where information can be meaningfully said to reside. It cannot be distributed through the interior in any straightforward way, because the interior is causally disconnected from the exterior. No signal, no particle, no quantum of information can travel from inside the event horizon to the outside. And if the black hole eventually evaporates into featureless thermal radiation that carries no information, then all of that entropy, all 10 to the 77th microstates worth of information, simply vanishes from the universe. This is not a minor bookkeeping error. This is 10 to the 77th missing entries in the cosmic ledger, an amount of information larger than the total information content of every star in every galaxy in the observable universe. Gone, without a trace, without a forwarding address. Something is wrong with our assumptions, not at the margins, at the core. The information paradox is not a puzzle about what happens in the impossibly distant future when a black hole finishes evaporating. It is a puzzle about the consistency of the fundamental laws of physics right now. Today, this moment, as Sagittarius A star sits at the center of our galaxy, as millions of stellar mass black holes drift silently through the Milky Way, as quasars blaze at the edges of the observable universe. If information is destroyed by black holes, then unitarity is violated now. The laws of physics, as we understand them, are inconsistent now. The paradox is not a future problem. It is a present tense emergency. Hawking himself spent nearly 3 decades defending the position that information is genuinely destroyed. In lectures, papers, and public debates, he maintained that black hole evaporation represents a true violation of quantum unitarity. He argued that the universe simply does not conserve information in the way physicists had long assumed. This was not idle speculation. It was a deeply considered, carefully argued position from one of the greatest theoretical physicists of the 20th century. He was not hedging. He was not speculating. He was reading the mathematics as honestly as he could, and the mathematics told him that information is lost, and it made him a minority of one among his peers. Because most physicists, particularly those working in string theory and quantum gravity, believed the opposite. They believed information must be preserved. They argued that Hawking's calculation, while correct in its broad strokes, was a semi-classical approximation that missed something essential. Some subtle mechanism, some quantum gravitational correction that becomes significant only in the deep infrared or at very late times, must encode the information in the Hawking radiation in a way that Hawking's calculation fails to capture. They believed this passionately, but proving it was another matter entirely. In 1997, Hawking formalized his position by making a famous bet with Kip Thorne against John Preskill of Caltech. Hawking and Thorne wagered that information falling into a black hole is permanently lost. Preskill wagered that it is somehow preserved. The stakes were an encyclopedia of the winner's choice, a symbol deliberately selected for the vast store of information at risk. The bet stood for 7 years. In 2024, at a conference in Dublin, Ireland, Hawking publicly conceded. He announced that he now believed information is preserved. He presented Preskill with a baseball encyclopedia, Total Baseball, the ultimate baseball encyclopedia. Thorne, his fellow betmaker, did not concede, and Hawking's proposed mechanism for how information escapes, involving a sum over topologies in the gravitational path integral, was not widely accepted by the community as a satisfying resolution. The paradox endured, deeper, more urgent, more unsettling than ever. But here is what makes this truly terrifying. The information paradox does not merely tell us that we are missing a detail somewhere. It does not point to a small correction that could be patched in. It tells us that one of the three foundations of modern physics, the equivalence principle, unitarity, or effective field theory, is wrong, not approximately wrong, wrong in principle, and after 50 years, we still do not know which one. There is a technical detail in Hawking's original calculation that is worth dwelling on, because it illuminates why the result is so robust and so difficult to evade. Hawking did not merely postulate that black holes radiate. He derived the result from first principles, using the well-established framework of quantum field theory. The key mathematical step involves what are called Bogoliubov transformations, a set of relationships that connect the definition of particle, as used by an observer in the distant past, before the black hole formed, to the definition of particle, as used by an observer in the distant future, long after the formation. In flat, empty spacetime, these two definitions agree. A vacuum for one observer is a vacuum for all observers, but in the curved spacetime produced by a collapsing star forming a black hole, the two definitions diverge. What the early observer calls a vacuum, empty space, devoid of particles, the late observer interprets as a thermal bath of particles. The Bogoliubov coefficients that mediate this transformation have a thermal character. They produce a Planck distribution. The result is Hawking radiation, and it follows inevitably from the combination of quantum field theory and general relativity. No additional assumptions are required. No exotic physics is invoked. The radiation emerges from the mathematical structure of the two most well-tested theory in physics, applied simultaneously to the same physical situation. This is why the paradox is so devastating. It is not the product of speculation. It is the product of calculation. To fully appreciate the timescales involved in black hole evaporation, it helps to place them in the context of the cosmic timeline, the future history of the universe, as predicted by current cosmological models. We are currently in what astrophysicists call the stelliferous era, the age of stars. Stars are still forming, still burning, still illuminating the cosmos. This era will not last forever. According to current models, the last stars in the universe, small dim red dwarfs, burning their hydrogen fuel with extraordinary frugality, will exhaust that fuel and go dark in roughly 10 to the power of 14 years. 100 trillion years from now. That sounds unimaginably distant. And it is. But on the timescale of black hole evaporation, it is nothing. It is a rounding error. The stars will have been dead for inconceivable ages before the first stellar mass black hole even begins to noticeably shrink. After the stars die, the universe enters what is sometimes called the degenerate era. The cosmos is populated by stellar remnants, white dwarfs cooling into black dwarfs, neutron stars spinning down, and black holes. Over timescales of 10 to the power of 20 to 10 to the power of 40 years, complex processes may further erode these remnants. Protons, if they decay, and some grand unified theories predict they do, with a half-life of roughly 10 to the power of 36 to 10 to the power of 41 years, would cause white dwarfs and neutron stars to slowly disintegrate into radiation and lighter particles. By 10 to the power of 40 years from now, all ordinary matter may have dissolved. Only black holes remain. And then, in the black hole era, stretching from roughly 10 to the power of 40 years to 10 to the power of 100 years, the universe is dominated by black holes. Slowly, imperceptibly, they evaporate. Stellar mass black holes, their Hawking radiation finally outpacing the ever-cooling cosmic background, shed their mass particle by particle over 10 to the power of 67 years. Supermassive black holes, the last substantial objects in existence, endure longer, the largest perhaps lasting until 10 to the power of 100 years or beyond. But eventually, even they are gone. The last black hole radiates its final photon, and the universe enters the dark era. an infinite, cold, empty expanse containing nothing but the fading whisper of Hawking radiation and a thin soup of photons and elementary particles, all drifting apart in an endlessly expanding void. It is in this context, this staggeringly vast cosmic timeline, that the information paradox plays out. The question is not academic. The question is about the ultimate fate of every piece of information in the universe. Because eventually, if current physics is correct, every piece of matter in the cosmos will either decay directly into radiation or be consumed by a black hole that subsequently evaporates. Either way, the information ends up in radiation. And if that radiation is thermal, if it carries no information, then the universe's final state is one of complete informational death. Every record erased, every history lost, every quantum state destroyed. The universe that once contained stars, galaxies, planets, and life would end as a featureless bath of thermal radiation, indistinguishable from the radiation produced by any other universe with the same total energy. The past would be truly, absolutely, irreversibly forgotten. This is the nihilistic endpoint that Hawking's calculation implies. And it is this endpoint, this total informational annihilation, that the unitarity of quantum mechanics forbids. Let us return to the three-principle conflict and examine more carefully why it is so excruciatingly difficult to resolve. The equivalence principle is not merely a useful approximation, it is the conceptual engine that generates all of general relativity. Einstein's great insight was that gravity is not a force in the Newtonian sense. It is a manifestation of the curvature of space-time, and the equivalence principle, the observation that a freely falling observer in a gravitational field cannot, by any local experiment, distinguish their situation from the absence of gravity, is what connects the mathematical framework of curved space-time to physical reality. Without it, there is no connection between the geometry described by Einstein's equations and the behavior of physical objects. Abandoning the equivalence principle does not merely modify general relativity, it removes its foundation. Unitarity, similarly, is not a peripheral feature of quantum mechanics. It is the architectural requirement that makes the theory coherent. A non-unitary theory of quantum mechanics is not a slightly different version of quantum mechanics. It is a fundamentally different kind of theory, one in which the probabilistic structure of the quantum world breaks down, in which measurement outcomes are not properly normalized, in which the past cannot be inferred from the future. There have been attempts to construct non-unitary theories. None have come close to replicating the predictive successes of standard quantum mechanics. An effective field theory, the framework of the standard model, is not an optional add-on. It is the language in which all of particle physics is written. Every prediction of the standard model, the existence of quarks and leptons, the masses of the W and Z bosons, the magnetic moment of the electron, the existence of the Higgs boson, is a prediction of effective field theory. To abandon effective field theory outside the event horizon is to abandon the framework that successfully describes every particle physics experiment ever performed. The paradox, then, is not a choice between a good option and a bad option. It is a choice between three catastrophes. Abandon the equivalence principle, and you lose general relativity. Abandon unitarity, and you lose quantum mechanics. Abandon effective field theory, and you lose the standard model. There is no painless exit. Every door leads to a demolition. This is why the information paradox has consumed the careers of so many brilliant people for so many decades. It is not merely difficult. It is structurally impossible to resolve within the existing framework. A resolution requires not just a new idea, but a new framework, one that subsumes and transcends both quantum mechanics and general relativity. A theory of quantum gravity. And that theory, despite decades of effort by thousands of researchers, remains undiscovered, and the human dimension of this struggle deserves recognition. The disagreement between Hawking and the rest of the theoretical physics community was not a polite academic difference. It was fierce, personal at times. Hawking was legendary not only for his brilliance, but for his stubbornness. He held his position for nearly 30 years in the face of mounting opposition. Opposition that included some of the most accomplished physicists alive. Leonard Susskind, who would become one of the key architects of the resolution, described the dispute as the most important in physics since the debates between Bohr and Einstein about the foundations of quantum mechanics in the 1920s and 30s. The comparison is apt. Just as the Bohr-Einstein debates forced the physics community to confront the foundational meaning of quantum mechanics, the information paradox forced a new generation to confront the foundational meaning of spacetime, gravity, and quantum information. Susskind, in particular, took Hawking's challenge personally. He has described the moment he first heard Hawking's argument as a turning point in his career. He felt, viscerally, that Hawking was wrong, that information could not be destroyed, that some mechanism must preserve it. But feeling was not enough. The burden of proof lay with those who claimed information survives. Hawking had the calculation. He had the mathematics. He had the clear, elegant logic of simple gravity on his side. Those who disagreed had to do more than assert their faith in quantum mechanics. They had to show how the information gets out. And for decades, no one could. The bet between Hawking, Thorne, and Preskill crystallized the stakes. An encyclopedia, a physical embodiment of organized information, wagered on whether the universe preserves or destroys the information that falls into its most extreme objects. The choice of stakes was not casual. It was symbolic. An encyclopedia is a compendium of human knowledge. The bet was about whether the universe has a compendium of its own, an indelible record of everything that has ever happened. When Hawking conceded in 2004, the reaction was mixed. Many physicists were gratified. The concession seemed to validate what most of the community had long believed, that unitarity is inviolable, that information survives. But Hawking's proposed mechanism, involving path integrals and topological sums, was vague and unsatisfying. It pointed in the right direction, perhaps, but it did not explain how the information gets out. It did not identify the specific error in his original 1974 calculation. It did not provide a concrete, calculable mechanism by which Hawking radiation encodes the information of the infalling matter. The concession was significant. The resolution remained elusive. Thorne's refusal to concede was also noteworthy. Thorne, a formidable physicist in his own right, he would share the Nobel Prize in Physics in 2017 for the detection of gravitational waves, felt that the case for information preservation had not been convincingly made. He did not believe information was necessarily destroyed, but he did not believe the evidence for its preservation met the standard required to settle the bet. As of the most recent public statements, Thorne has still not conceded. The bet, in a sense, remains open. And this brings us to the deepest, most unsettling implication of Section 3. The information paradox is not merely a puzzle about black holes. It is an indictment of the completeness of modern physics. It is telling us, loudly and unambiguously, that our two best theories, quantum mechanics and general relativity, are not just difficult to unify. They are mutually contradictory in a specific, well-defined, experimentally relevant context. They cannot both be correct as currently formulated. The paradox is not a curiosity. It is a crisis, and its resolution will require a revolution. But what exactly does that revolution look like? What are the specific proposals that physicists have put forward, and why has none of them fully succeeded? That is where we turn next. There is one more aspect of the information paradox that must be emphasized before we move on, because it is often underappreciated. The paradox is not only about what happens to information at the end of the evaporation process, that impossibly distant moment when the black hole finally winks out of existence. It is about what is happening right now, at every moment, to every black hole in the universe. Consider Sagittarius A star. It is not evaporating in any meaningful sense at present. It is absorbing far more from the cosmic background than it emits, but it is still emitting Hawking radiation, feebly, imperceptibly, and each Hawking photon that escapes carries with it a piece of the paradox. Is that photon correlated with the matter that formed the black hole 4 billion years ago? Is it entangled with the stars that fell in last millennium? Or is it genuinely thermal, truly random, truly devoid of any connection to the black hole's history? The answer to this question determines whether the foundations of physics are consistent or broken, and we do not have the answer. We have arguments, we have conjectures, We have partial calculations in simplified models, but we do not have a definitive, universally accepted resolution. The information paradox is, in this sense, the most important unsolved problem in theoretical physics, not because it is the most practical. It has no foreseeable technological applications, not because it is the most observable. The Hawking radiation from any astrophysical black hole is far too faint to detect with current or foreseeable instruments, but because it strikes at the heart of what physics is. Physics is the search for consistent, universal laws. The information paradox tells us that our current laws are not consistent, not in an abstract hypothetical sense, in a concrete, calculable, unambiguous sense. The laws contradict each other, and until we understand why and how to fix it, we do not truly understand the universe. The first serious attempt to resolve the information paradox was the most conservative. Perhaps, some physicists suggested, the information is simply not lost. Perhaps when a black hole evaporates down to the Planck scale, a mass of roughly 22 micrograms, a size of roughly 10 to the negative 33 centimeters, it does not vanish completely. Perhaps it leaves behind a remnant, a tiny stable relic, Planck-sized, containing all the information that ever fell in. The information is not destroyed, it is stored permanently, in a nugget so small that it would take 10 to the 20th of them, laid end to end to span a single proton. The proposal is called the remnant hypothesis, and it has a certain elegance. It requires no modification to quantum mechanics. It requires no modification to general relativity. The information survives, locked inside an object too small to decay further. The paradox is resolved, the universe's records are preserved, and nothing about the fundamental framework of physics needs to change. But here is the problem. A black hole can swallow an arbitrary amount of information. Throw in a star, and the black hole absorbs the star's complete quantum state, the positions, momenta, spins, and charges of every particle in that star. Throw in another star, and it absorbs that too. There is no upper limit on the number of distinct quantum states that can fall through the event horizon. A solar mass black hole, according to the Bekenstein-Hawking formula, has an entropy of roughly 10 to the 77th. A supermassive black hole has even more, and all of that information, all those microstates, would need to fit inside a Planck-sized remnant, an object 20 orders of magnitude smaller than a proton, containing more information than all the stars in the observable universe. This is not obviously impossible, but it creates a catastrophe of its own. If Planck-sized objects can have an essentially infinite number of internal states, then they can be produced in any sufficiently energetic process. Every high-energy particle collision would have a tiny but non-zero probability of creating a remnant. The number of distinct remnant species would be effectively infinite. Virtual remnant pairs would contribute to the calculation of every quantum process, introducing infinite corrections that cannot be controlled. This phenomenon is known as the pair production catastrophe. It does not merely create problems for the remnant idea, it undermines the predictive power of quantum field theory itself. The cure is worse than the disease. Most physicists, upon careful analysis, concluded that remnants do not resolve the paradox. They merely replace one catastrophe, the loss of information, with another, the breakdown of effective field theory. Some researchers continue to explore refined versions of the remnant idea, but it has fallen decisively out of the mainstream. The consensus is that black holes do not leave remnants, they evaporate completely, and the information must come out some other way. The second major approach was far more radical, and for nearly 2 decades, it was the dominant framework in theoretical physics. In 1993, the Dutch Nobel laureate Gerard Hooft proposed the concept of black hole complementarity. The idea was developed and championed by Leonard Susskind of Stanford, one of the founders of string theory, along with his collaborators Lars Thorlacius and John Uglum. Their proposal, published in a landmark paper that same year, fundamentally reframed the paradox in a way that no one had anticipated. Susskind's core insight was that the paradox arises because physicists were attempting to combine two descriptions that cannot coexist: the description of the black hole from the perspective of a distant observer, and the description from the perspective of an observer falling in. Complementarity asserts that both descriptions are valid, complete and self-consistent. But they are fundamentally different and mutually exclusive. No single observer can ever verify both simultaneously. The contradiction exists only in the mind of someone who tries to combine two incompatible frames of reference into a single picture. Here is the idea in detail. Consider a distant observer watching an object fall into a black hole. From their perspective, the infalling object never actually crosses the event horizon. It approaches the horizon, its light shifting redder and dimmer, appearing to slow down asymptotically. The distant observer sees the object, or rather, the information it carries, encoded on the horizon's surface, in what Susskind called the stretched horizon. The stretched horizon is a thin, hot membrane vibrating with quantum degrees of freedom that scrambles the infalling information and eventually re-emits it through Hawking radiation. From this external perspective, the information never enters the black hole. It is preserved on the horizon and returned to the universe through radiation. Unitarity is maintained. No information is lost. Now consider the infalling observer. They pass through the event horizon smoothly, noticing nothing unusual. The equivalence principle holds. There is no wall, no fire, no barrier. Physics at the horizon for the infalling observer is perfectly ordinary. They continue falling inward, experiencing the interior of the black hole, whatever that interior may contain, until they encounter the singularity. From their perspective, the information falls in and eventually is destroyed. The key to complementarity is that these two stories, information preserved on the horizon and information destroyed in the interior, are both correct. But they are correct for different observers, and no single experiment can reveal the contradiction, because the two observers can never compare their results. The infalling observer cannot send a message back out to the distant observer. The distant observer cannot jump in to check what the infalling one experienced. The contradiction is, in Susskind's phrase, operationally unobservable. And an unobservable contradiction, he argued, is not a contradiction at all. It is merely an artifact of trying to combine perspectives that physics itself forbids you from combining. This was a revolutionary proposal. It meant abandoning the assumption that there is a single, observer-independent reality. The interior of the black hole exists for the infalling observer, but not, in any operationally meaningful sense, for the distant one. The information on the horizon exists for the distant observer, but not for the infalling one. The universe, near a black hole, splits into complementary descriptions that cannot be unified. Complementarity drew inspiration from quantum mechanics itself. In quantum mechanics, the properties of a system depend on how you measure it. A photon's polarization is not determined until a measurement is made. The measurement context matters. Complementarity extended this principle to the structure of spacetime. The description of a black hole depends on who is doing the describing. For nearly 2 decades, complementarity was the dominant framework. It was elegant, self-consistent, and appeared to resolve the paradox without sacrificing any fundamental principle. All you had to give up was the notion of a single objective description of reality. And quantum mechanics had already primed physicists to give that up. Then, in 2012, the firewall argument detonated. 4 physicists, Ahmed Amhary, Donald Marolf, Joseph Polchinski, and James Sully, collectively known by their initials as AMPS, published a paper that exposed a fatal flaw in complementarity. Their argument, now known as the firewall paradox, is one of the most consequential results in theoretical physics in the past 30 years. It showed that the unobservable contradiction that complementarity relied upon is not unobservable at all. It can be localized to a single, well-defined physical question, and the answer to that question, whatever it is, destroys one of the 3 pillars. The AMPS argument proceeds as follows. Consider a black hole that has been evaporating for a long time, specifically past its page time. The page time, named after physicist Don Page, is the moment at which the black hole has emitted roughly half of its initial entropy. At this point, if unitarity holds, the already emitted Hawking radiation must be maximally entangled with the remaining black hole. The early radiation and the late radiation are correlated. The information is being transferred from the black hole to the radiation field. Now focus on a single outgoing Hawking particle emitted just after the page time. for unitarity to hold, for the information to be recoverable from the radiation, this outgoing particle must be entangled with the previously emitted radiation. The total radiation field must form a coherent quantum state in which the early and late emissions are correlated. But for the equivalence principle to hold, for the event horizon to be smooth and unremarkable, this same outgoing particle must be entangled with its ingoing partner, the particle that fell past the event horizon. The smoothness of the vacuum at the horizon requires this specific entanglement. Without it, the quantum state at the horizon is disrupted, the vacuum becomes excited, the horizon becomes a violent, high-energy boundary. Here is the crux. Quantum mechanics has a strict rule called the monogamy of entanglement. If particle A is maximally entangled with particle B, then particle A cannot simultaneously be entangled with a third particle C. Entanglement is exclusive. It cannot be shared. A single qubit cannot be maximally entangled with two different partners. The outgoing Hawking particle, therefore, faces an impossible demand. Unitarity requires it to be entangled with the early radiation. The equivalence principle requires it to be entangled with its ingoing partner. Monogamy forbids it from being maximally entangled with both. One of the entanglements must break. If the entanglement with the early radiation breaks, unitarity is violated. The information is not recoverable. The paradox persists. If the entanglement with the ingoing partner breaks, the vacuum at the horizon is disrupted. The equivalence principle is violated. The event horizon becomes a searing wall of ultra-high energy radiation, a firewall that incinerates anything attempting to pass through. The smooth, innocuous horizon predicted by general relativity does not exist. It is replaced by an inferno. The aim result forced a stark choice. Either unitarity fails, or the equivalence principle fails, or effective field theory outside the horizon fails. There is no option that preserves all three. And unlike complementarity, which argued the contradictions was unobservable, the Ames argument is direct. Is there a firewall at the horizon, or is there not? This question has a definite answer, and whatever that answer is, it shatters one of the pillars. The firewall paper sent shockwaves through the theoretical physics community. It was the most discussed paper in the field for years. Conferences were organized specifically to address it. Hundreds of response papers were written. Polchinski, one of the AMP's authors and among the most respected string theorists in the world, argued that firewalls are real, that the equivalence principle genuinely fails at the horizon of an old black hole. He maintained this position until his death from brain cancer in 2018. Susskind, whose complementarity framework had been directly challenged, acknowledged the severity of the problem. He called the firewall argument a genuine crisis and spent years searching for a resolution. One of the most dramatic responses came in 2013 when Juan Maldacena of the Institute for Advanced Study in Princeton and Susskind himself proposed a connection so radical that it defied immediate comprehension. They called it ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes. In 1935, Einstein and his collaborator Nathan Rosen showed that the Schwarzschild solution to general relativity could be interpreted as a bridge connecting two distant regions of space-time. This bridge is not traversable. Nothing can pass through it, no signal can be sent across it. But it exists as a feature of the space-time geometry, a tunnel linking two separate black holes or two separate regions of the same space-time. EPR refers to the Einstein-Podolsky-Rosen paradox, also published in 1935. Einstein, Podolsky, and Rosen used the phenomenon of quantum entanglement, the correlations between distant particles that persist regardless of the distance separating them, to argue that quantum mechanics must be incomplete. Einstein called it spooky action at a distance and found it deeply troubling. Maldacena and Susskind's proposal was stunning. They argued that these two phenomena, wormholes and entanglement, are not merely analogous. They are the same thing. Every pair of entangled particles is connected by a tiny, non-traversable wormhole. Every wormhole corresponds to entanglement between the systems at its two ends. The geometric structure of spacetime and the quantum correlations between particles are two faces of the same coin. Entanglement is geometry. Geometry is entanglement. The very fabric of spacetime is stitched together by quantum entanglement. If ER equals EPR is correct, the firewall paradox dissolves. The Hawking radiation emitted by the black hole is connected to the black hole's interior by a web of Einstein-Rosen bridges. The entanglement between the outgoing radiation and its ingoing partner is the same entanglement, viewed through the lens of space-time geometry, as the entanglement between the radiation and the previously emitted particles. The apparently separate entanglements are, geometrically, the same. The monogamy constraint is not violated because the wormhole structure unifies what appeared to be distinct entanglement relationships into a single, coherent geometric picture. The mathematical structure is striking. The proposal unifies two of Einstein's most famous 1935 papers, one on wormholes, one on entanglement, into a single framework, 80 years after they were published independently. It suggests that spacetime itself is woven from quantum entanglement, that the connectivity of space is a macroscopic manifestation of microscopic quantum correlations. This is not science fiction. It is a conjecture with increasing theoretical support. But it remains unproven. It has not been rigorously formulated within a complete theory of quantum gravity. It is at present a deep physical intuition dressed in the language of theoretical physics. Compelling, suggestive, beautiful, but not definitive. A separate and enormously influential thread in the information paradox story, predates the firewall debate by more than a decade. In 1997, Juan Maldacena, then a young physicist at Harvard, published a paper that would become the most cited in the history of theoretical physics. It proposed the anti-de Sitter conformal field theory correspondence known as AD-SCFT. The correspondence states that a theory of quantum gravity in anti-de Sitter space, a space-time with a constant negative cosmological constant, characterized by a saddle-like geometry, is exactly equivalent to a quantum field theory without gravity living on the boundary of that space-time. The theory in the bulk, the interior of the anti-de Sitter space, contains gravity, black holes, strings, curved space-time. The theory on the boundary, a lower dimensional surface wrapping the bulk, is a standard quantum field theory. No gravity, no space-time curvature, just quantum fields evolving unitarily on a fixed background. The boundary theory is manifestly unitary. Its evolution is described by a unitary operator. Probabilities sum to 1. Information is conserved. There is no information paradox in the boundary description. And since the boundary theory is exactly equivalent to the bulk theory, including the bulk's black holes, the bulk theory must also be unitary. Black hole evaporation, described in the bulk, must be a unitary process when translated to the boundary. Information cannot be destroyed. This was, within the framework of string theory in anti-de Sitter space, something close to a mathematical proof that information is preserved. The paradox is resolved, at least in anti-de Sitter space, not by identifying a specific mechanism, but by demonstrating the existence of a dual description in which the paradox cannot arise. The boundary theory simply does not have black holes. It does not have event horizons. It does not have singularities. And yet it contains all the same information as the bulk theory that does. There is, however, a significant caveat. Our universe is not anti-de Sitter. Observations indicate that our universe has a small positive cosmological constant. It is approximately de Sitter, not anti-de Sitter. The geometry is fundamentally different. Anti-de Sitter space has a time-like boundary at spatial infinity. De Sitter space has a space-like boundary in the future. Extending the AD-SCFT correspondence to de Sitter space, constructing what would be called DSCFT, remains one of the great open problems. Many attempts have been made. None have achieved the rigor, universality, or mathematical control of the original anti-de Sitter version. Whether the lessons of AD-SCFT apply directly to our universe is genuinely unknown. The holographic principle which undergirds AD-CFT offers another angle on the paradox. First proposed by 't Hooft in 1993 and refined by Susskind in 1995, the holographic principle asserts that the maximum information content of any region of space is proportional not to its volume but to its surface area, measured in Planck units. This means that the three-dimensional world we experience is, in a precise mathematical sense, a projection of information encoded on a two-dimensional surface. The interior of any region of space is not the fundamental description, the boundary is. The three-dimensional picture is emergent, derived, reconstructed from the boundary data. Think about what that means for a moment. The room you are in, the depth you perceive between yourself and the far wall, the space you move through. According to the holographic principle, these are not fundamental properties of reality. They are emergent properties, macroscopic consequences of the information encoded on a surface you cannot see or touch. The three-dimensionality of space is, in this framework, as much an illusion as the wetness of water is an illusion of molecular arrangement, real at the macroscopic scale, not present at the fundamental scale. The most recent and perhaps most exciting development in the information paradox arrived in 2019 and 2020 with a series of papers on quantum extremal surfaces and the island formula. Key contributors include Netta Engelhardt, Aaron Wall, Ahmed Almheiri, Thomas Hartmann, Juan Maldacena, Edgar Shagulian, and Ami Hossein Tajdini, among others. Building on the Ryu-Takayanagi formula, which relates the entanglement entropy of a boundary region in AD-SCFT to the area of a minimal surface in the bulk, these researchers derived a formula for computing the entropy of Hawking radiation that includes quantum gravitational corrections. The result reproduces the Page curve. Named after Don Page, who predicted its shape in 1993, the Page curve describes how the entanglement entropy of the Hawking radiation should evolve if information is preserved. Early in the evaporation, as the black hole emits radiation, the entropy of the radiation increases. More and more entangled particles are released. The radiation is becoming more disordered, more entangled with the remaining black hole. But at the Page time, roughly the halfway point of evaporation, the curve bends. The entropy begins to decrease. The late radiation starts becoming correlated with the early radiation. Information is being transferred. By the time the black hole fully evaporates, the total entropy of the radiation returns to zero. All the information has been recovered. The island formula reproduces this curve through a mechanism that is genuinely bizarre. At late times in the evaporation, the formula identifies islands, regions of the black hole interior that, for the purposes of computing the radiation's entanglement entropy, should be counted as part of the radiation's entanglement wedge. In other words, parts of the black hole's interior become, informationally speaking, part of the exterior, the boundary between inside and outside, which seemed absolute and permanent in the classical spacetime picture, shifts and blurs in the quantum gravitational calculation. This does not mean a distant observer can literally peer inside the black hole. It does not mean signals escape from behind the event horizon. What it means is that the quantum gravitational description of reality does not respect the clean division between inside and outside that the classical spacetime picture demands. The event horizon is, in the deeper description, not an absolute boundary. Information encoded in the interior is, through the entanglement structure, accessible in principle from the exterior. The prison is more porous than it appeared. The island formula has been celebrated as a major breakthrough. For the first time, it provides a concrete, calculable mechanism by which the Page curve is reproduced and information is preserved. But it has important limitations. The calculations have been performed primarily in two-dimensional models of gravity. Simplified toy models that capture essential features of the physics, but lack the full complexity of our four-dimensional universe. Extending the results to realistic four-dimensional spacetime remains formidable, and the formula relies on the gravitational path integral, a mathematical framework whose foundations are not fully understood and whose validity in certain regimes is debated. One more approach deserves attention. In 2016, Hawking himself, in collaboration with Malcolm Perry of Cambridge and Andrew Strominger of Harvard, proposed the concept of soft hair. The classical no-hair theorem, established in the 1960s and 70s, states that a black hole is completely characterized by just three numbers: its mass, its electric charge, and its angular momentum. Nothing else. Two black holes with the same mass, charge, and spin are identical, regardless of what fell into them. A black hole formed from a collapsing star is indistinguishable from a black hole formed from a collapsing cloud of antimatter, provided the three numbers match. The information about what went in, the detailed quantum state of the infalling matter is lost behind the horizon and invisible from the outside. Hawking, Perry, and Strominger challenged this picture. They showed that black holes carry additional, previously unrecognized quantum numbers, soft charges associated with the infinite dimensional symmetry group of the gravitational field at the event horizon. These soft charges, called supertranslation hair and superrotation hair, are subtle quantum mechanical properties that survive on the horizon even after all the classical hair has been accounted for. The black hole, they argued, is not as featureless as the no-hair theorem claimed. It has texture, delicate, quantum mechanical texture that could, in principle, encode information about what fell in. The soft hair proposal is intriguing. It opens a door that the no-hair theorem seemed to have sealed, but whether soft hair carries enough information to fully resolve the paradox remains an open question. Several independent analyses have argued that the soft charges, while real, do not contain sufficient degrees of freedom to encode the complete quantum state of an arbitrary collection of infalling matter. The soft hair is real. The door it opens may be too narrow. Let that register. 5 decades of effort. Some of the most brilliant minds in the history of science. Remnants, complementarity, firewalls, ER equals EPR, add SCFT, the holographic principle, the island formula, soft hair. Each proposal captures something real about the physics. Each illuminates a different facet of the paradox. And none, not a single one, has delivered a complete, universally accepted, fully rigorous resolution in realistic 4-dimensional space-time. The reason is as simple as it is humbling. Solving the information paradox almost certainly requires a complete theory of quantum gravity, a theory that unifies general relativity and quantum mechanics into a single, consistent, predictive framework. String theory is one candidate. Loop quantum gravity is another. Causal set theory, asymptotic safety, and various emergent gravity programs offer additional possibilities. But no candidate theory has yet been developed to the point where it can answer, definitively and without ambiguity, what happens to the information that falls into a 4-dimensional black hole in a universe with a positive cosmological constant. We have fragments, we have insights, we have mathematical structures that describe pieces of the answer in simplified settings, but the full theory, the master framework, remains beyond our grasp. Hawking's concession in 2004 was a landmark moment. His acknowledgement that information is preserved shifted the weight of opinion decisively, but his proposed mechanism was not accepted as a resolution, and Thorne, his fellow betmaker, still has not conceded. The paradox endures, and its persistence is not a sign of failure. It is a sign that we are approaching the boundary of human knowledge, the place where our best theories collide, where our deepest assumptions are tested, and where the next revolution in physics is hiding, waiting to be found. But something else was emerging from the struggle, not just a solution to a paradox, a new vision of reality itself. The implications of the firewall paradox deserve deeper exploration, because they reveal just how severe the crisis truly is. If firewalls are real, if the equivalence principle genuinely fails at the event horizon of an old black hole, the consequences extend far beyond the black hole itself. The equivalence principle is not some isolated postulate that applies only near black holes. It is the bridge between the mathematics of curved space-time and the physical experience of gravity. If it fails at a black hole's event horizon, there is no guarantee it will elsewhere. The failure might be specific to black holes, confined to the extreme conditions near an event horizon, but it might also signal a more general breakdown, a crack in the foundation that, once identified, reveals weaknesses throughout the structure. Several researchers have explored this possibility. If the equivalence principle breaks down at black hole horizons, does it also break down near cosmological horizons, the de Sitter horizon of our accelerating universe? Does it fail in other extreme gravitational environments? The questions are open. The implications are vast. Moreover, the firewall debate illuminated a deep tension between locality and gravity that had been lurking in the formalism for decades. Locality, the principle that physical interactions happen at specific points in space, that distant events cannot influence each other instantaneously, is one of the bedrocks of quantum field theory. But the firewall argument suggests that preserving unitarity in black hole evaporation may require non-local effects. The information inside the black hole must somehow influence the radiation outside, despite the causal separation imposed by the event horizon. This is not a signal traveling faster than light. It is something subtler, a quantum correlation that transcends the causal structure of classical spacetime, and it suggests that the notion of locality itself may be an approximation, valid in ordinary circumstances, but broken in the extreme environment of a black hole. The response to the firewall within the broader physics community revealed something fascinating about the sociology of theoretical physics. The community split roughly into camps. Those with backgrounds in general relativity tended to resist firewalls and defend the equivalence principle. Those with backgrounds in quantum information theory and string theory tended to accept the AMPS argument and explore its consequences. The debate was not purely technical. It involved deep commitments to different frameworks, different intuitions, and different visions of what the final theory should look like. In a field where definitive experiments are often impossible, you cannot build a black hole in a laboratory and test whether firewalls exist. The resolution ultimately depends on theoretical consistency, and theoretical consistency, it turns out, is a surprisingly elastic criterion when the stakes are this high. Let us return to the AD-CFT correspondence and examine its implications more carefully. Maldaceno's 1997 paper did not emerge from nowhere. It grew out of a long tradition of research in string theory, particularly the study of D-branes, extended objects in string theory on which open strings can end. Maldacena considered a stack of D-branes in the low energy limit and showed that the physics could be described in two equivalent ways: as a gravitational theory in the bulk anti-de Sitter space near the branes, or as a quantum field theory, specifically a supersymmetric Yang-Mills theory, on the world volume of the branes. The two descriptions are not merely similar, they are exactly equivalent. Every calculation in one description has a precise counterpart in the other. The correspondence has been tested in thousands of calculations. Quantities computed in the boundary field theory, correlation functions, entanglement entropies, thermodynamic properties, match the corresponding gravitational calculations in the bulk with extraordinary precision. In certain limits, the correspondence can be checked analytically. In others, it has been verified numerically. The evidence for its validity is overwhelming within the framework of string theory. For the information paradox, AD-SCFT provides the strongest argument, yet the information is preserved. The boundary theory is a standard quantum field theory. It has a Hilbert space, a Hamiltonian, and a unitary time evolution operator. There is no room for information loss. There are no event horizons. There are no singularities. The theory is manifestly well defined. And since it is equivalent to the bulk theory, which does contain black holes, event horizons, and singularities, the bulk theory must also preserve information. The paradox in the AD-SCFT framework is resolved not by identifying a mechanisms, but by demonstrating the existence of a framework in which the paradox cannot arise. The information is preserved because the dual description demands it. This argument has a certain blunt force that is both its strength and its weakness. Its strength is that it is rigorous within its domain. If AD-FT is correct, and the evidence is very strong, then information is preserved in anti-de Sitter space, period, full stop. But its weakness is that it does not explain how. It does not identify the error in Hawking's calculation. It does not tell us which of the three principles, equivalence, unitarity, or effective field theory, breaks down and how. It provides an existence proof without a construction. We know the information gets out. We do not know the mechanism by which it gets out. This is like proving that a locked room contains a hidden door without being able to find the door. The island formula partially addresses this limitation. By providing a calculable formula that reproduces the page curve, it offers a concrete mechanism, or at least a concrete mathematical description, of how information is transferred from the black hole to the radiation. The islands in the formula identify specific regions of the black hole interior whose information content is, from the perspective of the entanglement calculation, attributed to the exterior radiation. This is the first time in the history of the information paradox that a specific quantitative mechanism has been identified for information recovery. But the island formula raises its own questions. What does it mean, physically, for a region of the black hole interior to be part of the radiation's entanglement wedge? If a distant observer cannot access the interior, if no signal can cross the event horizon outward, in what sense does the interior information belong to the exterior? The answer appears to involve the distinction between classical and quantum descriptions. In the classical spacetime picture, the interior is inaccessible, but in the quantum gravitational description, the entanglement structure connects interior and exterior in a way that transcends the classical causal structure. The classical picture of an impermeable event horizon is, like so much else in this story, an approximation, a very good approximation in many regimes, but an approximation that fails subtly and profoundly when quantum gravitational effects are taken into account. The broader lesson of Section 4 is sobering. Half a century of work by extraordinary minds has produced extraordinary insights. Complementarity, holography, AD-CFT, firewalls, ER equals EPR, the island formula, soft hair. Each represents a genuine advance in understanding. Each has reshaped the landscape of theoretical physics, but none constitutes a complete, universally accepted resolution in the context that matters most. Our actual four-dimensional universe with a positive cosmological constant. The fragments of the answer are scattered across different frameworks, different approximations, and different spacetime geometries, assembling them into a coherent whole. A true theory of quantum gravity that resolves the paradox in full generality remains the central challenge of fundamental physics. And yet, from these fragments, a picture is beginning to emerge, a picture so radical, so counterintuitive, and so profound that it may represent the deepest truth physics has ever uncovered. There is one more angle worth exploring before we move on: the development of holographic entanglement entropy. The Ryu-Takayanagi formula and its generalizations deserves special attention because it provides the mathematical foundation on which the island formula is built, and because it reveals something extraordinary about the relationship between geometry and information. In 2006, Shinsei Ryu and Tadashi Takayanagi proposed a remarkable formula within the AD-CFT framework. They showed that the entanglement entropy of a region on the boundary, the amount of quantum entanglement between that region and the rest of the boundary, is given by the area of a minimal surface in the bulk that is anchored to the boundary of the region. The formula is strikingly simple. The entanglement entropy equals the area of the minimal surface divided by 4 times Newton's gravitational constant in natural units. The area of a geometric surface in the gravitational bulk encodes the entanglement structure of the quantum theory on the boundary. Think about that for a moment. A quantum informational quantity, entanglement entropy, which measures the degree of quantum correlation between two subsystems, is computed by a geometric quantity, the area of a surface in a gravitational spacetime. Information and geometry are linked. Quantum correlations and spatial surfaces are two descriptions of the same underlying reality. This is not a vague analogy. It is a precise quantitative formula confirmed by hundreds of calculations within AD-CFT. The Ryu-Takayanagi formula was generalized in subsequent years. In 2014, Engelhardt and Wall proposed the quantum extremal surface prescription, which extends the formula to include quantum corrections. Instead of finding the surface that minimizes the classical area, you find the surface that extremizes the sum of the classical area and the bulk entanglement entropy across that surface. This generalization is crucial for the information paradox, because it is the quantum corrections that distinguish the Page curve from the naively thermal Hawking calculation. Without the quantum corrections, the entanglement entropy of the radiation just keeps growing. The information appears lost. With the quantum corrections, the entropy follows the Page curve. The information is returned. The island formula is, in essence, the application of the quantum extremal surface prescription to the specific problem of Hawking radiation from an evaporating black hole. At early times, the quantum extremal surface sits near the event horizon, and the entropy of the radiation grows. At late times, after the Page time, a new extremal surface appears. the island surface located inside the black hole. This island surface has a smaller generalized entropy than the original surface. The formula instructs us to choose the surface with the smaller entropy, and so, at the page time, the dominant surface jumps from the one near the horizon to the island surface. The entropy of the radiation begins to decrease. The page curve is reproduced. The mathematical elegance of this result is remarkable. The physical interpretation is still debated, but the formula itself, its existence, its internal consistency, its agreement with the expectations from unitarity, represents one of the most significant theoretical advances in the study of quantum gravity in the past decade. It is worth pausing to note the irony embedded in this entire enterprise. The information paradox was created by Stephen Hawking in 1974. The tools that appear to be resolving it, the island formula, holographic entanglement entropy, the page curve, were developed decades later by researchers who were, in many cases, his intellectual descendants. Hawking himself participated in the resolution, proposing soft hair in his final major physics paper before his death in 2018. The paradox he created became the engine that drove theoretical physics forward for half a century. The crack he found in the foundation did not destroy the building. It revealed the need for a deeper foundation, and the search for that deeper foundation has produced insights that may ultimately be more revolutionary than anything Hawking himself imagined. The soft hair proposal, Hawking's final contribution, deserves one more moment of attention. The idea emerged from a re-examination of the symmetries of gravitational theory near null infinity and near black hole horizons. Strominger, working independently before joining forces with Hawking and Perry, had discovered that the gravitational S-matrix, the mathematical object describing how particles scatter in gravitational interactions, possesses an infinite dimensional symmetry group. These symmetries, called BMS symmetries after Bondi, Vanderburg and Metzner, who first identified them in the 1960s, generate conserved charges. And these charges, Hawking and his collaborators argued, are carried by black holes as soft hair, quantum numbers that survive on the horizon, and that could, in principle, distinguish between black holes formed from different initial states. The soft hair program is ongoing. It has generated a rich body of mathematical results. But the central question, whether soft hair carries enough information to resolve the paradox completely, remains unanswered. The no-hair theorem, it turns out, was not entirely wrong. It was incomplete. Black holes do have more structure than the theorem suggested. But whether that additional structure is sufficient to encode the complete quantum history of the infalling matter is a question that may require the full apparatus of quantum gravity to answer. And so we arrive at a crossroads. 5 decades of work, 8 major proposals, each one a monument to human ingenuity, each one a partial glimpse of a truth that remains, in its totality, hidden. The remnant hypothesis was elegant but catastrophic. Complementarity was revolutionary but incomplete. Firewalls was logically airtight but physically disturbing. ER equals EPR was beautiful but unproven. AD-SCFT was rigorous but restricted to the wrong spacetime. The holographic principle was radical but not yet experimentally confirmed. The island formula was calculable but confined to toy models. Soft hair was promising but potentially insufficient. The physicists who have devoted their careers to this problem are not discouraged by this state of affairs. They are energized by it, because the information paradox has done something extraordinary. It has taken a seemingly abstract question, what happens to information inside a black hole, and used it as a lever to pry open the deepest questions about the nature of reality. Questions about whether space is fundamental, questions about whether time is real, questions about whether the universe is, at bottom, made of information. The paradox has not been solved, but in the process of failing to solve it, we have learned more about the universe than we ever imagined possible. The information paradox is not, ultimately, a problem about black holes. It is a mirror, and what it reflects is a truth about the universe so deep that most people pass through their entire lives without encountering it. Consider what the paradox demands. It asks us to choose between the indestructibility of information and the smooth geometry of space-time, between the reversibility of quantum mechanics and the finality of gravitational collapse. Between the world as a quantum system with perfect memory and the world as a classical geometry with points of no return. These are not technical issues buried in the footnotes of a specialist paper. They are about the most fundamental features of reality, and the answer that has emerged, slowly, painfully, through decades of struggle, is that information wins, and space-time loses. This is the most radical outcome of the information paradox. It suggests that space-time itself is not fundamental, that the three-dimensional space you move through, the time you experience flowing from past to future, the distances between objects, the geometry of the cosmos, all of it is emergent, derived, built from something deeper, and that deeper something is quantum information. The evidence for this view comes from multiple independent directions, all converging on the same extraordinary conclusion. The Bekenstein-Hawking entropy formula tells us that the information content of a region of space is proportional to its surface area, not its volume. In a fundamental time, information should scale with volume. More space, more room for microstates. The area scaling is a signature of holography. It tells us the three-dimensional interior is not the fundamental description, the boundary is. The ADS-CFT correspondence makes this explicit. A universe with gravity, black holes, and space-time curvature is exactly equivalent to a quantum field theory on a lower dimensional boundary without gravity. The boundary is the fundamental description. The space-time with gravity is the emergent one. Event horizons, singularities, the geometry of the black hole interior, all emergent features of a deeper, gravitationless quantum system. The ER equals EPR conjecture pushes the idea further still. If entangled particles are connected by wormholes, and wormholes are geometric structures in space-time, then the fabric of space-time is knitted together by quantum entanglement. The connectivity of space, the fact that distant points are smoothly connected, is a consequence of the entanglement structure of the quantum state underlying the universe. Remove the entanglement, and the space disconnects. This is precisely what Mark van Ramsdonk demonstrated in a now celebrated thought experiment in 2010. Working within the ADS-CFT framework, van Ramsdonk considered two entangled quantum systems on the boundary. In the bulk, these systems correspond to two regions of spacetime, connected by a geometric bridge, an Einstein-Rosen bridge. Now gradually reduce the entanglement between the boundary systems. What happens to the bulk geometry? The bridge stretches. It becomes longer and thinner. The two regions of spacetime pull apart. The distance between them increases. Remove the entanglement entirely, and the spacetime disconnects completely. Two separate, unconnected regions of space. The fabric of the universe has been torn in two, not by any physical force, but by the reduction of quantum correlations on the boundary. Let that sink in. The distance between 2 points in space may not be a fixed, fundamental property of the universe. It may be a consequence of entanglement. More entanglement means shorter distance. Less entanglement means longer distance. No entanglement means the points are in different universes entirely. Space is a macroscopic manifestation of quantum correlations. It is not the stage on which quantum mechanics plays out. It is the product of quantum mechanics. This insight transforms the information paradox from a technical problem into a window onto the deepest nature of reality. The paradox forced physicists to ask whether information could be destroyed. The answer, almost certainly not, led them to question whether spacetime is fundamental. The answer, almost certainly not, led them to a vision of the universe as a quantum information processor, a system whose most basic constituents are not particles, not fields, not strings, not spacetime points, but qubits. Quantum bits, the simplest possible units of quantum information. The idea that the universe is, at bottom, made of information is sometimes called it from qubit, a phrase that echoes John Archibald Wheeler's earlier it from bit. Wheeler, the physicist who named black holes, spent the later decades of his career arguing that the physical world, the it, arises from information, the bit. He saw measurement and observation as the fundamental acts from which reality is built. Every physical quantity, he argued, derives its meaning ultimately from the information required to specify it. The modern version of this vision replaces classical bits with quantum bits, and observation with entanglement. But the depth of the it from qubit vision goes far beyond a slogan. If spacetime is emergent from quantum information, then every feature of spacetime is emergent. The event horizon of a black hole is not a fundamental boundary. It is a feature of the emergent description. In the deeper, information-theoretic description, there may be no boundary at all. The distinction between inside and outside the black hole may be an artifact of the spacetime picture, a feature of the map, not the territory. This is exactly what the island formula suggests. At late times, parts of the interior are informationally accessible from the exterior. The boundary blurs. The map loses accuracy. And if the boundary between inside and outside is not fundamental, then neither is the notion of a point of no return. The event horizon, the defining feature of a black hole, may be an emergent illusion. In the spacetime description, nothing escapes. In the deeper description, the information was never truly trapped. It was always encoded in the exterior, in the radiation, in the entanglement structure. The prison is not a prison. It is a hologram of a prison. This leads to one of the most profound concepts to emerge from the information paradox: scrambling. A black hole is not, in the quantum informational picture, a destroyer of information. It is a scrambler, the most efficient scrambler in nature. When information falls into a black hole, it does not sit quietly at the center or remain localized in any way. It is instantly and thoroughly mixed with all the other information the black hole contains. The scrambling happens in the minimum time allowed by the laws of physics, a time called the scrambling time, which is proportional to the mass of the black hole multiplied by the logarithm of its entropy. For a solar mass black hole, this is a tiny fraction of a millisecond. By the time you could blink, the information about any object that fell in has been spread across all the degrees of freedom of the black hole, smeared across the entire horizon, mixed so thoroughly that recovering it would require capturing and decoding every single Hawking photon the black hole will ever emit over its entire lifetime. Numbers so large, spread over a duration so vast, that no conceivable civilization could accomplish the task. The mathematical framework for understanding scrambling comes from quantum chaos, the study of how quantum systems lose track of their initial conditions. A key quantity is the Lyapunov exponent, which measures the rate at which initially similar quantum states diverge. In classical chaos, the Lyapunov exponent governs how quickly a tiny change in initial conditions grows into a large difference in later behavior, the famous butterfly effect. In quantum chaos, the analogous quantity describes how quickly quantum information spreads across the degrees of freedom of a complex system. In 2015, Maldacena, Stephen Schenker, and Douglas Stanford conjectured, and in many cases proved, that there is a maximum Lyapunov exponent for any quantum system at a given temperature, an upper bound on chaos, a speed limit for scrambling, and black holes saturate this bound. They are maximally chaotic. No physical system in nature can scramble information faster than a black hole. The universe has a speed limit for disorder, and black holes run at exactly that limit. This maximal chaos is deeply connected to the thermodynamics of black holes. The Bekenstein-Hawking entropy is enormous, far larger than the entropy of any conventional matter that could occupy the same volume. If the black hole is a quantum scrambler, the entropy measures the number of ways the information could be distributed across the black hole's internal degrees of freedom. It is a measure of scrambling capacity, and the area scaling, entropy proportional to area rather than volume, is a direct consequence of the holographic nature of the underlying quantum gravity theory. There is another angle that deserves careful attention. The information paradox has profound implications for the arrow of time. In everyday experience, time has a direction. Entropy increases. Eggs break and do not unbreak. Milk mixes into coffee and does not unmix. This thermodynamic arrow of time is a statistical phenomenon. It arises because there are enormously more high entropy states than low entropy states, so any system left to itself will almost certainly evolve toward higher entropy. But the fundamental laws of physics, both quantum mechanics and general relativity, are time reversible. They do not distinguish past from future. The Schrödinger equation runs equally well forward and backward. Einstein's field equations have no preferred time direction. The arrow of time is emergent, not fundamental, And the unitarity of quantum mechanics guarantees that this time reversal symmetry is exact. No information is lost. Every process can, in principle, be undone. The information paradox threatens this picture directly. If black holes destroy information, there are processes that genuinely cannot be undone. The arrow of time becomes absolute, fundamental, built into the laws of physics at the deepest level. The time reversal symmetry of quantum mechanics is broken. Not approximately, not statistically, but exactly. Most physicists find this prospect deeply troubling, not for aesthetic reasons, but because breaking unitarity unravels the entire mathematical structure of quantum mechanics. Unitarity, time reversal symmetry, and information conservation are all facets of the same mathematical property. Abandon one, and you abandon them all. And quantum mechanics, lest we forget, is the most precisely confirmed theory in the history of human science. Its predictions have been verified in every experiment ever performed. Its mathematical structure is elegant, consistent, and immensely powerful. Abandoning it to accommodate a semi-classical calculation about black hole radiation, a calculation that explicitly ignores quantum gravitational effects at the very point where they matter most, is, for the overwhelming majority of theoretical physicists, unthinkable. And so the consensus has shifted, slowly, reluctantly, but decisively. The majority of theoretical physicists now believe that information escapes from black holes. The Hawking radiation is not truly thermal. It carries subtle correlations, quantum correlations that encode the information of the infalling matter. These correlations are unimaginably difficult to detect. They are buried in the entanglement structure of the radiation, distributed across an astronomical number of particles emitted over the black hole's entire lifetime. But they are there, hidden, encoded, preserved. The Hawking radiation looks thermal because the information is scrambled, mixed so thoroughly that any measurement short of capturing every single quantum of radiation would fail to detect the correlations. The black hole is not a fireplace that destroys the book. It is a shredder that reduces the book to confetti so fine that reassembling it would take a computation larger than the universe. The information survives, but it is hidden behind the most impenetrable encryption the universe can produce. The implications cascade outward. If space-time is emergent from quantum information, then the singularity at the center of a black hole is not a place where reality ends. It is a place where the emergent description, the space-time map, breaks down. The deeper information theoretic description continues. There is no singularity in the fundamental theory. There is only a region where the map fails, and the territory must be described in a different language, the language of quantum information, qubits, and entanglement. What that description looks like, what replaces the singularity, is one of the great unsolved questions. Some approaches in string theory suggest a highly excited, string-scale structure. Loop quantum gravity suggests a quantum bounce. Other approaches propose entirely different pictures. We do not know which, if any, is correct. But the information paradox has taught us that asking, what happens at the singularity, may be the wrong question. The right question is, what does the quantum information look like in the regime where the spacetime approximation fails? The singularity is not a catastrophe of physics. It is a catastrophe of description, a failure of the map, not a failure of the territory. The universe, at its deepest level, is a quantum system, and quantum systems conserve information. They do not forget, they cannot forget. The mathematical structure of quantum mechanics forbids it. What the information paradox has revealed, through half a century of extraordinary effort, is that preserving information comes at a price. The price is space-time itself. To save the records, we may have to accept that space is not what we thought, that time is not what we assumed, that the three-dimensional world we perceive is a shadow, a macroscopic approximation of a deeper, fundamentally different reality described in the language of quantum information. The universe keeps its records, but the filing system is nothing like what anyone imagined. Let that sink in again, from a different angle. Consider the event horizon of a black hole, the boundary that defines the object, the surface from which nothing escapes. In the classical picture of general relativity, the event horizon is absolute. It is a one-way membrane embedded in space-time. Cross it, and you are gone. No signal you send will ever reach the outside. No information about your crossing will ever be available to an external observer. The event horizon is the ultimate point of no return. But in the quantum informational picture, the event horizon is not absolute. It is emergent. It is a feature of the spacetime description, a description that is itself an approximation of a deeper quantum reality. In that deeper reality, the information that crosses the horizon is not trapped. It is scrambled and encoded in the Hawking radiation through quantum correlations that span the entire exterior. The information is not behind a wall. It is woven into the fabric of the radiation itself, in a pattern so subtle and so complex that no local measurement could detect it, but so mathematically precise that it is, in principle, fully recoverable. There is no way out in the spacetime description. But in the quantum informational description, there was never a cage. This has a strange and beautiful implication. The most terrifying object in the universe, the place from which nothing escapes, the cosmic prison, the gravitational point of no return, may be terrifying only because we are using the wrong description. In the language of quantum information, the black hole is not a trap. It is a processor, an extraordinarily efficient processor that takes the information of everything that falls in, mixes it with breathtaking thoroughness, and slowly, over eons and epochs, releases it back into the universe through Hawking radiation. The information is never lost, but it is hidden behind a veil of scrambling so thorough that the universe itself would need to serve as the computer to decode it. This is not science fiction. This is the direction in which a significant and growing portion of the theoretical physics community is moving. Annual conferences with titles like It from Qubit and Quantum Information and Space-Time bring together researchers from quantum information theory, string theory, condensed matter physics, and general relativity to explore this emerging synthesis. The information paradox is the engine driving it forward. Without the paradox, the connection between quantum information and space-time geometry might never have been discovered. The crisis created the insight. The contradiction generated the understanding. Consider what this means for the singularity, the point of infinite density at the center of every black hole, the place where general relativity breaks down and the equations produce nonsensical answers. In the emergent spacetime picture, the singularity is not a physical catastrophe. It is a descriptive catastrophe. It is the place where the spacetime map, the emergent, approximate description of reality, built from quantum information, ceases to be accurate. The underlying quantum state does not become singular. It does not become infinite. It does not break down. Only the description breaks down. The map fails. But the territory continues. What replaces the singularity in the fundamental description? This is one of the great open questions of physics. In string theory, the singularity may be resolved by the finite size of strings, fundamental objects with a length scale of approximately 10 to the negative 33 centimeters. At the singularity, the curvature reaches the string scale, and the point-like description of particles breaks down. The strings see a different geometry, one that is smooth and well-defined where the classical geometry is singular. In loop quantum gravity, the singularity is replaced by a quantum bounce, a region of extreme but finite curvature where quantum gravitational effects halt the collapse and potentially reverse it. Some researchers have speculated that the interior of a black hole might connect, through the singularity, to a new region of space-time, perhaps even a baby universe. Others have proposed that the singularity is replaced by a fuzzy, quantum mechanical region with no classical geometric description at all. We do not know which of these pictures, if any, is correct. But the information paradox has taught us something invaluable. The singularity is not a fundamental feature of reality. It is an artifact of an approximate description. It is a sign that we need a better map, not that the territory is broken. The concept of emergent spacetime also transforms our understanding of entropy. In classical thermodynamics, entropy is a measure of disorder, of the number of microscopic configurations consistent with a macroscopic state. In the context of black holes and the holographic principle, entropy takes on a deeper meaning. The Bekenstein-Hawking entropy of a black hole is not just a count of internal microstates. It is a measure of the entanglement between the black hole and the rest of the universe. It is a measure of how much the black hole is connected, through quantum correlations, to the exterior world. When a black hole evaporates and its entropy is transferred to the Hawking radiation, what is happening is not the destruction of order. It is the redistribution of entanglement. The quantum correlations that were concentrated in the black hole are spread out across the radiation field. The total entanglement, the total amount of quantum correlation in the universe, is conserved. Nothing is created, nothing is destroyed. The cosmic ledger balances, but the form of the correlations changes. They go from being concentrated and localized, associated with a single massive object, to being dispersed and delocalized, spread across a vast cloud of radiation. The information is preserved, the entropy is conserved, and the universe, at its most fundamental level, remains a closed quantum system with a definite unitary evolution. There is a philosophical dimension here that is worth pausing on. The information paradox has forced physicists to confront a question that sits at the intersection of physics and philosophy. What is the universe made of? For centuries, the answer seemed clear. The universe is made of matter and energy, distributed through space and time. Space and time were the stage. Matter and energy were the actors. Physics was the study of how the actors behave on the stage. The information paradox has overturned this picture. The stage is not fundamental. Space and time are not the bedrock of reality. They are emergent, constructed from something deeper. And that deeper something is not matter or energy in any conventional sense. It is quantum information. Qubits, entanglement, correlations. The universe is not a collection of things distributed through space. It is a web of quantum correlations from which the illusion of space and the illusion of things distributed through it emerges. This is a paradigm shift of the first order. It is comparable in scope to the Copernican revolution, the realization that the Earth is not the center of the universe, or the quantum revolution, the realization that the microscopic world is fundamentally probabilistic. The information revolution, if it is borne out, will be the realization that the macroscopic world, the world of space, time, distance, and duration, is not fundamental. It is a projection, a hologram, a shadow on the wall of Plato's cave, cast by the flickering light of quantum information. The universe does not care about our intuitions. It does not care that the event horizon appears to be a point of no return. It does not care that the radiation appears thermal. It does not care that the singularity appears catastrophic. The universe, at its deepest level, is a quantum system, and quantum systems do not forget. They preserve information with absolute, unyielding fidelity. The laws of physics guarantee it. The mathematics demands it. And the black hole, the object that seemed designed to destroy information, is the object that taught us information is indestructible. The universe keeps its records, but the filing system is nothing like what we imagined. It is not a library of books shelved in an orderly room. It is a vast, entangled web of quantum correlations, distributed across the entire cosmos, encoded in patterns so subtle that only the universe itself has the capacity to read them. The records are there. Every event, every interaction, every particle that ever existed, all preserved, all encoded, all waiting, in the quantum state of the universe, for no one in particular to read them back. And there is one final dimension to the deeper truth that deserves exploration. The information paradox has implications not just for the nature of space and time, but for the nature of knowledge itself. Consider what the paradox has taught us about the relationship between observation and reality. In classical physics, the universe exists objectively, independent of any observer. Space is there, time flows, objects have definite properties. The universe does not care whether anyone is watching. Quantum mechanics complicated this picture by introducing the role of measurement. The act of observation appears to collapse the wave function, selecting a definite outcome from a superposition of possibilities. But even in standard quantum mechanics, the underlying quantum state evolves unitarily, deterministically, and objectively. The wave function is real, even if its relationship to observation is mysterious. The information paradox and its tentative resolutions complicate this picture further. if space-time is emergent, if the three-dimensional world is a holographic projection from a lower dimensional boundary, then the reality we observe is not the fundamental reality. It is a derived, approximate, perspective-dependent description. The complementarity proposal took this to its logical extreme. The description of a black hole depends on who is doing the describing. The infalling observer and the distant observer see fundamentally different realities. Neither is wrong, neither is privileged. The universe, near a black hole, does not have a single objective description. This is not merely a restatement of quantum measurement theory. It is a deeper and more radical claim. In quantum mechanics, different observers can disagree about the outcome of a measurement, but they agree on the underlying quantum state. In the black hole context, complementarity suggests that different observers may disagree about the quantum state itself, about whether information is inside or outside the black hole, about whether the interior exists or does not exist. The notion of an observer-independent reality, already stressed by quantum mechanics, appears to break down entirely in the presence of an event horizon. Whether this is the correct interpretation remains debated. Some physicists believe that a complete theory of quantum gravity will restore a single objective description, that complementarity is an approximation, not a fundamental feature. Others believe that observer dependence is built into the fabric of reality at the deepest level. The debate is ongoing, but it is a debate that could not have occurred without the information paradox. The paradox forced the question. And the question, what is the objective content of reality, may be the deepest question physics has ever asked. There is also the question of what the information paradox means for the far future. If the universe continues to expand, driven by the cosmological constant, then eventually every structure in the cosmos will be dismantled. Stars will die, galaxies will disperse, black holes will evaporate, and all the information in the universe, every quantum state of every particle that ever existed, will be encoded in a thin, cold bath of radiation, spread across an exponentially expanding void. The information will be preserved. Unitarity guarantees it, but it will be dispersed so thoroughly, encoded in correlations so complex, that no physical process, not even in principle, could reconstruct any particular piece of it in a finite time. This is the ultimate fate of information in a universe with a positive cosmological constant. Not destruction, dispersal, not erasure, dilution. The cosmic records persist, but they become, for all practical purposes, unreadable. The universe remembers everything, but in the far future it whispers the memories so softly, across distances so vast, that no listener could ever hear them. The information paradox began as a question about black holes. It became a question about the nature of space-time. It ended, or rather it continues, as a question about the nature of reality itself. And the answer, as it stands, is more strange, more beautiful, and more unsettling than anyone who first posed the question could have imagined. Step back now. Let the weight of what the information paradox has revealed settle into place. A single calculation, published in 1974 by a young physicist working alone at the University of Cambridge, set in motion a chain of discoveries that has reshaped our understanding of space, time, gravity, and information. From one paper about radiation from a dying black hole, we have arrived at the possibility that space-time itself is woven from quantum entanglement, that the three-dimensional world is a holographic projection from a lower dimensional boundary, that the universe is, at its core, a quantum information processor of almost inconceivable complexity, that black holes are not destroyers but scramblers, nature's most efficient data processors, hiding information behind a veil of quantum chaos so thorough that no finite computation could penetrate it, that the singularity is not an endpoint but a failure of description, that the fabric of reality is not made of matter, or energy, or even space. It is made of correlations, relationships, entanglement, quantum bits that know about each other across distances that have no meaning in the deeper description. What does this mean for us? For human beings standing on a small rocky planet, orbiting an unremarkable star, in one of hundreds of billions of galaxies, in a cosmos that may itself be the emergent shadow of a deeper quantum reality. It means, first, that the universe is far stranger than it appears. The everyday world, the solid table, the empty room, the ticking clock, is not what it seems. Beneath the familiar three-dimensional experience lies a fundamentally different kind of reality, one in which distance and duration are not primitive, one in which the distinction between here and there may be emergent from the correlations of quantum bits on a boundary we cannot see or touch. The information paradox did not merely reveal a problem about black holes. It cracked open the surface of reality and showed us a glimpse of what lies beneath. And what lies beneath is not particles arranged in space. It is information arranged in patterns of entanglement from which the illusion of space and everything in it emerges. Second, it means that the human capacity for understanding is itself something extraordinary. Consider the situation. We are biological organisms on a small planet. Our minds evolved to navigate a world of moderate scales, moderate temperatures, moderate sizes, moderate speeds. We were not designed to understand the quantum informational substrate of space-time. We were not designed to manipulate the mathematics of Bogoliubov transformations, holographic entanglement entropy, or quantum extremal surfaces. And yet, through the patient accumulation of mathematical insight spanning centuries, from Newton to Einstein to Schwarzschild to Penrose to Hawking to Bekenstein to Susskind to Maldacena, we have arrived at the doorstep of a revelation about the deepest nature of reality. A species that measures time by the rising and setting of its nearest star has deduced that time itself may not be fundamental. A species that navigates space by the movement of its limbs has deduced that space itself may be emergent. There is something staggering about this, something that should not be taken for granted. Third, the information paradox reminds us of the limits of what we currently know. For all the progress, complementarity, holography, add-CFT, the island formula, ER equals EPR, the paradox is not fully resolved. We do not yet possess a complete theory of quantum gravity. We do not know with mathematical precision the mechanism by which information escapes a realistic four-dimensional black hole in a universe with a positive cosmological constant. We do not know whether the holographic principle extends beyond anti-de Sitter space. We do not know whether ER equals EPR is correct in full generality. We do not know what replaces the singularity at the center of a black hole. We are standing at the edge of human understanding, looking out into a darkness that our most powerful theoretical tools have only begun to illuminate. But perhaps the most profound implication of the information paradox is what it says about the nature of the universe itself. The universe keeps records, indestructible, unalterable records. Every interaction, every collision, every transformation, every event, no matter how violent, how extreme, how cosmically catastrophic, is recorded in the quantum state of the universe. Nothing is erased. Nothing is forgotten. The universe has perfect memory. This is not a comforting statement. It is not a statement about meaning or purpose. The universe does not care whether the information it preserves is important or trivial, beautiful or ugly, significant or meaningless. It preserves all of it with the same absolute fidelity, not because it values memory, not because it cares about records, but because the fundamental mathematical structure of reality, the unitarity of quantum mechanics, requires it. Information conservation is not a choice the universe makes. It is a constraint the universe obeys. A structural feature of reality, as basic and as inescapable as the conservation of energy. And there is a strange and beautiful poetry in the fact that this truth was revealed to us by black holes, the most destructive objects in the cosmos, the ultimate devourers, the places from which, so we thought, nothing returns. It was precisely by studying these objects that we discovered the universe's deepest commitment, that nothing is truly lost. The destroyers revealed the indestructibility. The places of apparent annihilation taught us about preservation. The paradox of information loss led us to the discovery of information's permanence. There is no way out, we said. Nothing escapes a black hole. And that remains true in the space-time description. But the space-time description is not the final word. Beneath it, in the quantum substrate, the information endures, scrambled beyond any practical hope of recovery, dispersed across a radiation field spanning timescales that dwarf the current estimated age of the universe, but intact, complete, preserved with the same absolute fidelity that the universe applies to every atom, every photon, every quantum state it contains. The information paradox asked a simple question: can the universe forget? And after 50 years of struggle, 50 years of brilliant proposals, devastating counter-arguments, and hard-won insights, the answer appears to be no. The universe is a system with perfect recall, and we are part of that system. Every atom in your body carries the imprint of its history. Every photon that has ever bounced off your skin carries information about you into the cosmos. And according to the deepest principles of physics, the principles that Hawking's paradox forced us to examine, to question, and ultimately to reaffirm, that information will persist, not because anyone will read it, not because it matters to the cosmos, but because the laws of physics do not permit its destruction. Think about that for a moment. You are not merely an observer of the universe. You are a participant in its informational structure. Your existence is recorded, not in any meaningful narrative sense, but in the quantum state of every particle that has ever interacted with you. The universe does not tell your story, but it preserves the data from which your story could, in principle, be told. And nothing, not time, not entropy, not even a black hole, can erase that data. Fourth, and perhaps most sobering, the information paradox reveals the depth of what remains unknown. We do not know whether the universe is truly holographic. We do not know whether ER equals EPR is the correct description of the entanglement geometry connection. We do not know whether the island formula survives extension to 4 dimensions. We do not know what the complete theory of quantum gravity looks like, or whether string theory, loop quantum gravity, or some as-yet unimagined framework will ultimately provide the answer. The paradox has illuminated the path forward, but the destination remains hidden in the distance, shrouded in mathematical difficulty and conceptual uncertainty. Every answer we have obtained has generated new questions. Every resolution has revealed new layers of mystery. The universe, it seems, does not give up its secrets easily. It demands that we earn them through decades of painstaking mathematical work, through the collision and synthesis of ideas from different traditions, through the willingness to abandon cherished assumptions when the evidence demands it. The paradox also forces a reckoning with the nature of scientific progress itself. For most of the 20th century, physics advanced through a productive cycle. Theorists would propose ideas, experimentalists would test them, and the interplay between theory and experiment would drive the field forward. The information paradox breaks this cycle. The Hawking radiation from any astrophysical black hole is so faint, so unimaginably below the threshold of any detector we can build or even conceive of building, that direct experimental verification of the paradox's resolution is impossible for the foreseeable future. We cannot measure the correlations in Hawking radiation. We cannot check whether firewalls exist. We cannot verify whether the interior of a black hole is smooth or singular. This means the information paradox must be resolved by theoretical consistency alone, by the demand that our equations be internally coherent, that our frameworks be mathematically sound, that our principles be mutually compatible. This is a different kind of physics, closer in spirit to mathematics than to traditional experimental science. It requires a different kind of confidence, not the confidence that comes from seeing a needle move on a dial, but the confidence that comes from watching a mathematical structure click into place with a coherence that could not be accidental. Whether this kind of confidence is sufficient to resolve the paradox is itself a deep question, a question about the epistemology of physics, about how we know what we know, and about what counts as knowledge in a domain where experiments are impossible. Some physicists find this situation troubling. They worry that theoretical physics, untethered from experiment, will drift into mathematical speculation, beautiful structures that have no connection to the actual universe. Others argue that the situation is not so different from the early days of general relativity. When Einstein published his field equations in 1915, the experimental evidence was slim, a single anomaly in the orbit of Mercury. It took decades before the theory was thoroughly confirmed by observation. The theoretical framework came first, the experiments followed. Perhaps the same will be true for quantum gravity. Perhaps the theoretical resolution of the information paradox will guide us to predictions that can eventually be tested. Predictions about gravitational wave signatures, about the cosmic microwave background, about the behavior of quantum systems in extreme conditions that we have not yet imagined. There is also a profoundly human dimension to this story that deserves acknowledgement. The information paradox has not been solved by a single genius working in isolation. It has been solved, or rather, it is being solved, by a community. Hundreds of physicists spread across dozens of countries, working across decades. Each contribution builds on the last. Bekenstein's entropy formula enabled Hawking's radiation calculation. Hawking's radiation enabled the information paradox. The paradox enabled complementarity. Complementarity's failure enabled the firewall argument. The firewall argument enabled ER equals EPR, and all of it together enabled the island formula. The history of the information paradox is a history of collaborative intellectual effort on a scale that is rarely appreciated. No one person could have done it alone. The paradox is too deep, too multifaceted, too technically demanding for any single mind. It required the collective intelligence of a generation, and it will require the collective intelligence of the next generation to finish the job. We began this journey with a question that sounds simple enough to ask in a single sentence. What happens to the information that falls into a black hole? The answer led us through the deepest waters of modern physics, through the mathematics of Hawking radiation and the temperature of dying black holes, through the entropy inscribed on event horizons by Bekenstein, through the singularity theorems of Penrose and the gravitational collapse calculations of Oppenheimer and Snyder, through the bold reframing of complementarity and the devastating precision of the firewall argument, through the speculative grandeur of ER equals EPR and the mathematical power of AD-SCFT, through the revelations of the island formula and the tantalizing hints of soft hair, through the emerging vision of a universe built not from space-time but from quantum information, a universe where distance is entanglement, where geometry is correlation, where the fabric of reality is woven from quantum bits. And at the end of this journey, the answer appears to be, yes, the universe remembers, the information survives, not in the way we imagined, not stored in a vault behind the event horizon, not carried out by a messenger particle, not written on a visible surface that any instrument could read. It is encoded in the Hawking radiation, in the correlations between photons emitted over the black hole's entire lifetime, in the entanglement structure that connects every quantum of radiation to every other quantum in a single, coherent record of everything the black hole consumed. The information is there, but is scrambled so thoroughly, mixed so completely, that recovering it would require a computational effort beyond anything any civilization could ever undertake. The universe keeps its records, but it does not make them easy to read. This truth was not easy to find. It took half a century. It consumed the professional lives of some of the most brilliant physicists in human history. It drove Hawking to reverse his position after 30 years of defending the opposite view. It drove Polchinski to propose that the interior of a black hole might be an inferno of high-energy particles. It drove Maldacena to discover the most important duality in the history of theoretical physics. It drove Susskind to argue that reality depends on who is observing it. It forced an entire generation of physicists to question whether space-time, the stage on which all of physics plays out, is the fundamental entity they had always assumed it to be. And the paradox is not yet fully resolved. The tools we have are powerful but incomplete. The island formula works in simplified models. The AD-CFT correspondence works in a space-time that is not our own. ER equals EPR is a conjecture that awaits rigorous proof. Soft hair is promising but may be insufficient. No single framework has delivered the final, definitive resolution in realistic four-dimensional space-time in a universe with a positive cosmological constant. The last chapter of this story has not been written. Perhaps that is fitting. The information paradox has always been a story about the limits of knowledge, about the boundary between what we understand and what we do not, about the courage required to confront a problem so deep that solving it may require rebuilding the foundations of physics from the ground up. The black hole does not care about our theories. It does not care about our debates. It sits at the center of its galaxy, patient and silent, warping the space-time around it with a gravity that no equation yet written can fully describe. Its event horizon glows faintly with Hawking radiation, a radiation so dim that it will not be measured by any instrument humanity currently possesses or is likely to possess for centuries to come. Its interior hides a singularity, or whatever replaces the singularity in the true theory of quantum gravity that we have not yet found. But the universe keeps its records. This is the lesson the information paradox has taught us. Not because the universe cares about records, not because the universe values memory, but because the fundamental laws of physics, the laws that govern every particle, every field, every interaction, every event in the cosmos, are structured in such a way that information cannot be destroyed. It can be hidden, it can be scrambled beyond any hope of practical recovery. It can be dispersed across the cosmos in ways that would take longer than the current estimated age of the universe to decode. But it cannot be erased. The mathematical structure of reality forbids it. Stephen Hawking created the paradox. He was the first to see the crack in the foundation. He followed the mathematics with unflinching honesty, even when it led to a conclusion that violated one of the deepest principles of physics. He defended that conclusion for nearly 30 years against the opposition of the majority of his peers. And he was wise enough, in the end, to change his mind when the evidence shifted. His legacy is not the paradox itself. His legacy is the revolution in understanding that the paradox set in motion. A revolution that is still unfolding, still deepening, still revealing new layers of a reality more strange and more profound than anyone dared to imagine. We still live in the early days of that revolution. The full implications of the information paradox have not been worked out. The complete theory of quantum gravity remains undiscovered. The true nature of the black hole interior remains unknown. The relationship between quantum information and space-time geometry is partially understood at best. The deep questions, what is space made of? Why does time flow? What replaces the singularity? Remain open, but we know more than we did. We know the universe has perfect memory. We know space-time is probably not fundamental. We know the quantum world and the gravitational world are connected in ways that Einstein never imagined and that Hawking only began to uncover. And we know that the answer to the paradox, the real, final, complete answer, when it comes, will reshape our understanding of what the universe is. There is a black hole at the center of our galaxy. Right now, it has consumed stars. It has swallowed gas clouds and dust and light. Matter has fallen past its event horizon that will never return to the visible universe. And according to the deepest principles of physics, we have been able to uncover principles tested and confirmed across every domain of science, refined and deepened by the information paradox itself. It has forgotten nothing. Every atom, every photon, every quantum state, all recorded, all preserved, all waiting, encoded in the faintest whisper of Hawking radiation. A radiation that will take longer to read than the stars will shine, for the universe to read them back. The information paradox is not just about black holes. It is about whether the universe keeps its promises, whether the laws of physics are truly inviolable, whether the past is truly written in a language that cannot be unwritten. And the answer, as far as we can tell, is yes. The universe does not forget. It never has. And as long as the laws of physics hold, it never will. That is the truth Hawking found, alone in his office at Cambridge, half a century ago. And it is more terrifying, more beautiful, and more strange than anything he or anyone ever expected. Somewhere right now, a black hole is evaporating, particle by particle, photon by photon. Each quantum of Hawking radiation carries with it a whisper, a fragment of entanglement, a thread of correlation, a piece of the record. And together, across timescales that dwarf the age of stars, that dwarf the age of galaxies, that dwarf any duration the human mind was built to comprehend, those whispers will reconstruct the story of everything the black hole consumed. Not because anyone is listening, not because the story matters to anyone, but because the laws of physics will not allow the story to be forgotten. Nothing is lost. Nothing is destroyed. Nothing is erased. The universe remembers. The darkness at the center of a black hole is not emptiness. It is not a void. It is not the end. It is a library. Encrypted beyond comprehension, scrambled beyond recovery, sealed behind a horizon that only the patient passage of cosmic time can open. But a library nonetheless, complete, intact, permanent. This is the truth that a quiet calculation in 1974 set in motion. This is the truth that 50 years of extraordinary intellectual effort has painstakingly uncovered. This is the truth that the information paradox, the greatest unsolved problem in theoretical physics, has been trying to tell us all along.